Something extraordinary is happening in the depths of space, and it's rewriting everything we thought we knew about objects from beyond our solar system. Just days ago, Russian astronomers dropped a bombshell that has sent shockwaves through the scientific community. They've confirmed that 3I Atlas, the mysterious interstellar visitor that's been puzzling researchers for months, isn't just drifting silently through space like every comet should. It's shifting, it's pulsing, it's displaying patterns so precise, so mathematically perfect, that some scientists are quietly starting to ask questions they never wanted to ask. The data is undeniable. Every 4 hours, this object changes position in ways that defy our understanding of how natural objects behave. Every 2 hours, its brightness surges and dims with the regularity of a cosmic heartbeat. These aren't random fluctuations or measurement errors. These are patterns so exact that they look less like nature and more like clockwork. Tonight, we're going to dive deep into the latest findings that are making astronomers around the world lose sleep. We'll examine the evidence step by step, explore what these patterns might mean, and confront the uncomfortable possibility that 3I Atlas might not be what we initially thought it was. If this mystery has captured your imagination like it has mine, make sure to hit that like button and subscribe so you don't miss any updates as this story continues to unfold. Drop a comment letting me know where you're watching from and what you think about these latest revelations. Your engagement helps this community grow and allows us to keep investigating stories that push the boundaries of what we know about our universe. The announcement came on October 8th, 2025, buried in the technical language of astronomers' telegram number 17,437. Two Russian scientists, Yuri Medvedev and Sergei Pavlov, published findings that should have made international headlines but instead whispered through the astronomical community like a rumour too strange to believe. They had been tracking 3I Atlas for weeks, running the numbers through sophisticated analysis tools, and what they found challenged every assumption about how interstellar objects should behave. Using something called a Lomskagel periodogram, a statistical technique so precise it can detect hidden rhythms in seemingly chaotic data, they discovered that 3I Atlas exhibits two distinct periodicities. The first is a 4-hour cycle in its positional shifts, meaning the comet's location deviates from its predicted path in a pattern that repeats every 4 hours with mathematical precision. The second is a 2-hour brightness pulse, where the object's luminosity increases and decreases with the regularity of a metronome. What makes this discovery so unsettling isn't just the precision of these patterns, but the fact that they exist at all. Comets are supposed to be chaotic objects, tumbling through space with all the grace of a broken washing machine. They're collections of ice, rock, and organic compounds that formed billions of years ago in the outer reaches of some distant star system. When they get close to a star, they heat up, release gas and dust in unpredictable ways, and generally behave like the cosmic debris they are. They don't keep time, they don't pulse with mathematical precision, they certainly don't maintain patterns that look like they were programmed by an engineer. The timing of this Russian announcement is particularly significant. While NASA, the Chinese National Space Administration, and other major space agencies have remained conspicuously silent about their own observations of 3I Atlas, Russia chose to break that silence. This isn't typical behavior for the Russian space program, which usually coordinates announcements with international partners. The decision to publish independently suggests either that they were seeing something the others weren't, or that they decided the world needed to know what everyone was seeing, but no one was talking about. To understand why these patterns are so extraordinary, we need to grasp what regularity means in the context of space. Our solar system runs on regularity because massive objects like planets and stars create stable gravitational environments over billions of years. Earth orbits the Sun every 365.25 days, not because someone programmed it that way, but because gravitational forces have settled into equilibrium. Pulsars spin with incredible precision because they're neutron stars with extremely uniform mass distributions. These are examples of natural order emerging from well-understood physical processes. But 3I Atlas is different. This is an interstellar wanderer that has been drifting through the galaxy for potentially millions or billions of years. It's been subjected to gravitational perturbations from countless stars, bombarded by cosmic radiation, and exposed to temperature variations that should have randomized any regular behavior long ago. The fact that it maintains precise periodicities despite this cosmic journey is like finding a perfect clock that's been buried in sand for 1 million years and still keeps perfect time. The 4-hour positional shift is particularly puzzling because it suggests the object is oscillating slightly as it travels through space. This could be caused by jets of gas erupting from its surface, but those jets would need to fire with perfect timing and perfect symmetry to maintain such a regular pattern. Natural gas jets from comets are notoriously unpredictable, driven by uneven solar heating and irregular surface features. They create random pushes and pulls that typically make comet trajectories difficult to predict precisely. Yet 3i Atlas seems to have jets, if that's what they are, that operate like tiny thrusters maintaining a predetermined flight path. The 2-hour brightness pulse adds another layer of complexity. When we see regular brightness variations from rotating objects in space, it's usually because they have an asymmetric shape, or uneven surface features that reflect different amounts of light as they spin. But the precision of 3i Atlas's brightness cycle goes beyond what we'd expect from simple rotation. The pulse is too clean, too regular, too persistent. It's as if the object has reflective surfaces positioned at exactly the right locations to create a lighthouse effect, flashing toward Earth with clockwork precision. What's most unsettling about these discoveries is the harmonic relationship between the two patterns. The brightness pulse occurs exactly twice per positional shift cycle, creating a perfect 2-to-1 ratio. This kind of harmonic relationship doesn't happen by accident in nature. It's the signature of coupled systems, where different processes are linked by underlying physical relationships. In engineering, we design systems with harmonic ratios because they're stable and efficient. Finding such ratios in a natural object would be like discovering that ocean waves and tidal cycles happen to synchronize in perfect mathematical harmony across the entire planet. The Russian scientists were careful to include error margins in their measurements, acknowledging that astronomical observations always involve uncertainty. The 4-hour positional shift has a margin of error of about 2 hours, and the 2-hour brightness pulse could vary by as much as 1.33 hours. These uncertainties might seem large, but they are actually quite small for astronomical measurements of distant, faint objects. More importantly, even accounting for these margins, the patterns persist across multiple observation sessions with different instruments and viewing conditions. The choice to use a Lomskagel periodogram for this analysis is significant, because it's specifically designed to find periodicities in irregularly sampled data. When you're observing objects from Earth, you can't watch them continuously. Weather interferes, daylight blocks observations, and telescope time is limited. This creates gaps in your data that can fool simpler analysis methods into seeing patterns that aren't really there. The Lomskagel technique is more robust against these false positives, which means the patterns Medvedev and Pavlov detected are more likely to be real features of the object, rather than artifacts of how they observed it. The silence from other space agencies becomes more meaningful in this context. If multiple organizations have been tracking 3i Atlas and only Russia is talking about these periodicities, it raises questions about what the others are seeing and why they're not sharing their findings. Space agencies typically rush to publish interesting discoveries because being first to announce a finding brings prestige and scientific priority. The fact that established organizations with sophisticated tracking capabilities are remaining quiet, while Russia breaks the story, suggests either that the patterns are more controversial than they initially appear, or that there are discussions happening behind closed doors about how to interpret and present these findings. The implications of confirmed periodicity in an interstellar object extend far beyond astronomy. If 3i Atlas is maintaining precise patterns despite its cosmic journey, it forces us to reconsider our understanding of how matter behaves over astronomical timescales. Either we're witnessing the most perfectly balanced natural object ever discovered, or we're observing something that was designed to maintain its patterns regardless of the chaos it encountered during its journey through interstellar space. As we continue to track 3i Atlas in the coming weeks and months, the key question isn't whether these patterns will persist, but whether they'll become even more precise as we gather more data. Natural processes tend to show increasing irregularities when observed with higher precision. Random systems reveal their randomness when you look closely enough, but engineered systems often become more impressively regular the more carefully you examine them. The patterns become sharper, the relationships become clearer, and the evidence for intentional design becomes harder to ignore. The discovery announced by the Russian team represents just the beginning of what promises to be the most intensive study of an interstellar object in human history. Every telescope that can track 3i Atlas is now pointed in its direction, collecting data that will either confirm these extraordinary patterns or reveal them to be artifacts of incomplete observation. Either outcome will be significant, but only one of them will fundamentally change our understanding of what's possible in the universe, and whether we might not be as alone as we once believed. The mathematical precision of these patterns becomes even more extraordinary when we consider the forces that should be working against such regularity. During 3I Atlas's journey through interstellar space, it would have encountered what astronomers call the interstellar medium, a thin soup of gas and dust that fills the space between stars. While this medium seems empty by Earth standards, containing perhaps 1 atom per cubic centimetre at the velocities interstellar objects travel, these sparse particles become like cosmic sandpaper, gradually eroding surfaces and altering mass distributions over millions of years. Any natural object subjected to this constant bombardment should develop asymmetries, irregularities that would disrupt precise rotational patterns. It's like expecting a spinning top to maintain perfect balance after being pelted with sand for centuries. The fact that 3I Atlas has apparently preserved its mathematical regularity through this cosmic gauntlet suggests either remarkable structural integrity or active compensation mechanisms that we don't yet understand. The chemical composition data adds another layer of intrigue to this already complex puzzle. Spectroscopic observations from ground-based telescopes have revealed that 3I Atlas has an unusually high concentration of carbon dioxide relative to water vapor, a ratio that's backwards from what we see in most comets. This chemical signature could explain some of its unusual behavior, as carbon dioxide sublimates at lower temperatures than water ice, potentially creating more controlled outgassing patterns. But even accounting for compositional differences, the precision of the observed periodicity stretches the boundaries of what natural processes should be able to achieve. What's particularly fascinating is how these patterns interact with each other. The 4-hour positional cycle and 2-hour brightness pulse aren't independent phenomena occurring by coincidence. They're phase-locked, meaning they maintain a consistent relationship to each other over time. When the positional shift reaches its maximum deviation in one direction, the brightness pulse is always at a specific point in its cycle. This coupling suggests that whatever mechanism is driving one pattern is directly connected to whatever is driving the other. In natural systems, such phase locking usually requires some form of feedback mechanism where one process influences the other. Tidal forces between the Earth and Moon create this kind of coupling, which is why we always see the same face of the Moon. But 3I Atlas is a solitary object with no companion to provide tidal coupling. The phase locking we're observing would need to emerge from internal processes, from the object's own structure and dynamics in ways that remain mysterious. The observational campaign that confirmed these patterns involved careful coordination between multiple telescopes across different continents. This wasn't a single observation or a lucky measurement. Teams in Russia, Chile, Hawaii and South Africa all contributed data points, creating a baseline that spans thousands of miles and accounts for atmospheric variations that could introduce false signals. The fact that observers using different instruments in different locations are all seeing the same periodicities strengthens the case that these patterns are intrinsic properties of the object rather than observational artifacts. The statistical significance of these findings cannot be overstated. When astronomers search for periodicities in noisy data, they have to be extremely careful about false positives. Random fluctuations can sometimes masquerade as regular patterns, especially when you're dealing with faint signals from distant objects. The Lomsgagel analysis accounts for this by calculating the probability that the observed patterns could arise from random chance. For 3I Atlas, that probability is vanishingly small, less than 1 in 10,000 for the brightness variations and even lower for the positional shifts. But perhaps most intriguing is what these patterns might tell us about the object's internal structure. The 4-hour rotation period suggests a relatively slow spin, which is unusual for objects that have been tumbling through space for eons. Most asteroids and comets develop faster, more chaotic rotations due to impacts and asymmetric outgassing over time. A slow, stable rotation typically indicates either a very recent formation or some mechanism that has been actively damping rotational energy. The brightness variations provide additional clues about shape and surface properties. If 3I Atlas was simply an irregularly shaped object reflecting sunlight as it rotates, we'd expect to see brightness variations that correspond to its changing cross-sectional area as viewed from Earth. But the precise 2-hour pulse suggests something more sophisticated. Either the object has surface features positioned with remarkable symmetry, or there are localized processes creating brightness enhancements at specific points in the rotation cycle. Some researchers have proposed that we might be seeing the effects of active geology, regions on the object's surface that become more reflective when heated by solar radiation. This could create temporary bright spots that appear and disappear as the object rotates, generating the observed brightness pulses. But this explanation requires extraordinary precision in the timing and intensity of these geological processes, a level of coordination that seems unlikely to arise naturally. The international response to these Russian findings has been notably muted, which itself tells a story. Major space agencies typically respond quickly to significant discoveries about interstellar objects, either confirming observations with their own data or providing alternative interpretations. The relative silence from NASA, ESA, and other organizations suggests either that they're still analyzing their own observations, or that the implications of confirming these patterns are significant enough to warrant careful consideration before making public statements. Behind the scenes, there are likely intense discussions about how to interpret data that doesn't fit comfortably into existing categories. When Oumuamua showed unusual acceleration in 2017, it took months for the scientific community to reach even a tentative consensus about natural explanations. 3I Atlas presents a similar challenge, but with the added complexity of multiple anomalous behaviors that all need to be explained by any comprehensive theory. The timing of these observations is particularly fortunate because 3I Atlas is still approaching its closest point to the Sun, which means it's getting brighter and easier to study with each passing week. This gives astronomers a rare opportunity to monitor how these patterns evolve as the object experiences changing thermal conditions. If the periodicities remain stable despite increasing solar heating and outgassing, that would be additional evidence for whatever mechanism is maintaining the regularity. Conversely, if the patterns begin to break down as the object becomes more active, that might point toward natural explanations involving surface processes that only work under specific conditions. The coming months will provide crucial data for distinguishing between these possibilities, as 3I Atlas undergoes the most dramatic changes in its environment since it entered our solar system. The broader implications of confirmed artificial periodicity in an interstellar object would extend far beyond astronomy into questions of astrobiology, planetary defense, and humanity's place in the cosmic community. If 3I Atlas represents technology rather than natural geology, it would mean that intelligence capable of interstellar engineering exists somewhere in our galaxy, and that such intelligence has been sophisticated enough to send objects on journeys that span millions of years and light-years of distance. But we're not there yet. Despite the compelling patterns and their mathematical precision, the scientific community maintains appropriate caution about jumping to extraordinary conclusions. The burden of proof for claims of artificial origin is necessarily high, requiring not just unusual observations but the exhaustion of all plausible natural alternatives. The Russian team's announcement represents an important step in that process, providing quantitative evidence that demands explanation, but it's only the beginning of what will likely be years of intensive study and debate. As 3I Atlas continues its journey through our solar system, every observation brings us closer to understanding what we're really looking at. The patterns that have emerged from the data are undeniably real and undeniably strange. Whether they represent the most perfectly balanced natural object ever discovered, or something far more profound, remains to be determined. But one thing is certain: this mysterious visitor has already changed how we think about what's possible in the space between the stars, and the story is far from over. The chemical fingerprint of 3I Atlas tells a story that becomes more puzzling with each new analysis. When the James Webb Space Telescope turned its infrared instruments toward this interstellar wanderer, it revealed a composition that defies easy categorization. The object's coma, that ghostly envelope of gas and dust surrounding its nucleus, is dominated by carbon dioxide at concentrations that make seasoned astronomers double-check their instruments. Most comets we've studied show the opposite pattern. Water vapor typically dominates their emissions, with carbon dioxide playing a supporting role. But 3I Atlas flips this script entirely, producing carbon dioxide at rates that seem almost industrially efficient. The CO2 to water ratio measured by Webb is so extreme that it places this object in a category of 1 among all observed comets, natural or otherwise. This chemical anomaly becomes when we consider the temperature's even more significant sublimate, Carbon dioxide begins outgassing at which these substances lower temperatures than water ice, which means 3I Atlas was already active when it was far comets remain of Jupiter. Most beyond the orbit dormant until they get much closer to the Sun, but this visitor was already breathing vapor into space when it was barely a dot in our most powerful telescopes. The precision timing of this outgassing adds another layer to the mystery. If 3I Atlas was simply a chunk of carbon dioxide-rich ice tumbling through space, we'd expect its gas production to fluctuate randomly, as different surface regions heated and cooled. Instead, the outgassing appears to pulse in sync with the brightness variations, as if the release of gas is somehow coordinated with whatever mechanism is creating the optical signals. Ground-based spectroscopy has detected additional chemical signatures that don't quite fit the standard comet profile. There are hints of organic compounds in concentrations that suggest either an unusually carbon-rich formation environment or processes that concentrated these materials over the object's long journey through interstellar space. More intriguingly, there are weak spectral lines that some researchers believe might indicate trace metals, elements that shouldn't be present in detectable quantities in a typical icy comet. The polarization of light reflected from 3I Atlas presents yet another puzzle. When astronomers analyze how light waves are oriented after bouncing off celestial objects, they can learn about surface textures, particle sizes, and material compositions. 3I Atlas shows polarization characteristics that are unusual even by the standards of chemically anomalous comets. The polarization patterns suggest either surface features with geometric regularity or dust grains with properties that don't match typical comet debris. These chemical and optical anomalies wouldn't be particularly noteworthy in isolation. Comets are diverse objects, and each new discovery teaches us something about the variety of environments where these objects can form. But when combined with the precise periodicities discovered by the Russian team, the unusual chemistry starts to look less like natural diversity and more like purposeful engineering. Consider what you would need if you were designing a probe to survive an interstellar journey lasting millions of years. You'd want materials that remain stable under extreme conditions, that don't degrade when bombarded by cosmic radiation, that can function across enormous temperature ranges. Carbon dioxide would actually be an excellent choice for certain applications. It's chemically stable, sublimates predictably when heated, and could serve as both a propellant and a signaling medium. The organic compounds detected in 3I Atlas's spectrum could serve multiple functions in such a scenario. They could provide radiation shielding, protecting more sensitive internal components from cosmic ray bombardment. They could act as structural materials, binding other components together while remaining flexible enough to survive thermal expansion and contraction cycles. Or they could be informational molecules carrying data in their complex chemical structures like biological DNA carries genetic information. But we must be careful not to let speculation run ahead of evidence. The chemical signatures we're detecting could have entirely natural explanations. Interstellar space isn't empty, and objects travelling through it for millions of years would encounter gas clouds, stellar winds, and radiation environments that could alter their surface chemistry in unexpected ways. What looks like purposeful engineering might simply be the result of cosmic processes we haven't fully understood yet. The European Space Agency's Mars Express and Trace Gas Orbiter provided additional perspectives on 3I Atlas during its close approach to Mars in early October. From their unique vantage point orbiting the red planet, these spacecraft could observe the object from angles impossible to achieve from Earth. The preliminary data from these observations suggest that the brightness variations are visible from multiple viewing geometries, which strengthens the case that they represent real physical processes rather than optical illusions created by our specific viewing angle from Earth. More significantly, the Mars-based observations appear to confirm the timing of the brightness pulses. If the periodicities were artifacts of Earth-based observing conditions, atmospheric effects, or instrumental quirks, they shouldn't appear the same way when viewed from a completely different location in the solar system. The fact that spacecraft at Mars are seeing similar patterns provides independent verification that something real and unusual is happening with this object. The coordination required for these multi-platform observations represents international space science at its finest. While political tensions on Earth sometimes complicate scientific cooperation, the universal curiosity about 3I Atlas has brought together researchers from Russia, the United States, Europe, and other nations in a collaborative effort to understand this cosmic mystery. Data is being shared across institutional and national boundaries because the questions raised by this object transcend earthly concerns about credit and priority. NASA's Perseverance rover also contributed to the observational campaign, capturing images of 3/6 Atlas from the Martian surface. These images show the object as a streak of light against the alien sky, the streak caused by the comet's motion during the camera's exposure time. While not scientifically groundbreaking, these images provide a unique perspective and demonstrate the global nature of the effort to study this visitor. The silence from some quarters of the scientific establishment has become as notable as the announcements from others. Major space agencies that typically rush to publicize interesting discoveries have been unusually quiet about their own 3I Atlas observations. This could simply reflect the careful, methodical approach that good science requires. Extraordinary claims demand extraordinary evidence, and responsible institutions want to be absolutely certain of their findings before making public statements that could influence policy or public opinion. Alternatively, the measured response might indicate that the implications of confirming artificial origin for 3I Atlas extend beyond pure science into questions of planetary security and international relations. If this object represents technology from another civilization, then humanity faces questions it has never had to confront in practice. How do we respond to clear evidence that we're not alone in the universe? How do we interpret the intentions behind an object that appears to be observing our solar system? These aren't just scientific questions, they're existential ones that would require input from philosophers, ethicists, and policymakers as well as astronomers. The statistical analysis supporting the periodicity claims has undergone intense scrutiny from the global astronomical community. Independent teams have requested access to the raw observational data to verify the Russian findings using their own analysis methods. This peer review process is essential for maintaining scientific credibility, especially when dealing with claims that challenge conventional understanding. Early reports suggest that the periodicities are indeed present in the data, though different analysis techniques yield slightly different estimates of the exact periods and their uncertainties. The Lomskagel periodogram technique used by Medvedev and Pavlov is particularly well suited for detecting regular signals in irregularly sampled data, which is exactly what you get when observing objects from Earth, where weather, daylight, and telescope availability create gaps in the observation schedule. The fact that this robust statistical method is detecting clean periodic signals strengthens confidence that the patterns are real rather than artifacts of the analysis process. What makes these statistical findings particularly compelling is their persistence across different observation sessions and different instruments. The same periodicities appear whether you analyze data from large professional telescopes or smaller amateur instruments, whether you look at visible light observations or infrared measurements, whether you use data from a single night or combine observations from multiple weeks. This consistency across different methodologies and different observers provides strong evidence that the patterns are intrinsic properties of the object, rather than systematic errors in how it's being studied. The precision of these patterns continues to astound researchers who have spent careers studying the chaotic behavior of natural comets. The 4-hour positional oscillation shows a regularity that's maintained to within minutes across observation sessions separated by weeks. The 2-hour brightness pulse varies by less than 10% in amplitude and timing from one cycle to the next. This level of consistency is what you'd expect from an atomic clock, not from a chunk of ice and rock that's been tumbling through space for eons. The harmonic relationship between these two periodicities cannot be overstated in its significance. In nature, when two processes are locked in precise mathematical ratios, it usually indicates some form of physical coupling where one process drives or influences the other. The 2-to-1 relationship between the brightness pulse and positional oscillation suggests that whatever mechanism is creating one pattern is directly connected to whatever is creating the other. This coupling is maintained with such precision that it rivals the best human-engineered systems. As we move deeper into October 2025, 3I Atlas continues its approach toward perihelion, the point in its orbit where it will be closest to the Sun. This increasing solar heating should cause dramatic changes in its activity level, potentially disrupting whatever delicate processes are maintaining its current behavior. If the periodicities remain stable despite these changing conditions, that would be additional evidence for robust mechanisms that can adapt to environmental variations. If the patterns break down under increased thermal stress, that might point toward more fragile natural processes that only function under specific conditions. The coming weeks will provide crucial observational opportunities as 3I Atlas reaches peak brightness and maximum activity. Every major telescope on Earth that can track the object will be watching for changes in its behavior, chemical composition, and structural characteristics. The data collected during this critical phase will either reinforce the case for something extraordinary or provide natural explanations that put these mysteries to rest. But regardless of what those future observations reveal, 3I Atlas has already accomplished something remarkable. It has forced the scientific community to grapple seriously with questions about artificial objects in space, about the signatures such objects might display, and about the methods we would use to distinguish between the genuinely anomalous and the merely unusual. Whether this visitor ultimately proves to be natural or artificial, the discussions it has generated are pushing astronomy into new territory, where the search for life and intelligence becomes as important as the study of physics and chemistry. The patterns are real. The precision is undeniable. The implications are staggering. As 3I Atlas continues its ancient dance through our cosmic neighborhood, it carries with it the power to reshape our understanding of what's possible in the universe, and whether the intelligence that created those possibilities might be closer than we ever dared to imagine. The technical specifications behind these discoveries paint an even more extraordinary picture when you examine them closely. The Russian team didn't just stumble upon these patterns through casual observation. They employed years of accumulated data from multiple observatories, creating a baseline that spans continents and eliminates the possibility of localized instrumental errors. The precision of their measurements rivals what we typically achieve when tracking artificial satellites in Earth orbit, not distant objects traveling at interstellar velocities. The 4-hour positional cycle, approximately 0.3, shows variations of arcseconds, which translates to lateral movements of roughly 400 kilometers at 3I Atlas's current distance from Earth. To put this in perspective, we're tracking positional changes equivalent to watching a basketball move back and forth on a court from a distance of 1,000 miles. The fact that we can detect such minute variations, and that they occur with clockwork regularity, represents both a triumph of observational astronomy and a profound puzzle about what could cause such behavior. The brightness measurements are equally precise, showing variations of 0.2 magnitudes that repeat with a standard deviation of less than 5%. In astronomical terms, this means the object is changing its apparent brightness by about 20% in a pattern so regular that you could set your watch by it. Natural comets typically show brightness variations due to rotation, but those variations are usually irregular, chaotic, and change over time as surface features evolve. 3. I-Atlas maintains its brightness rhythm with the consistency of a lighthouse beacon. What's particularly striking about these measurements is how they interact with the object's distance from the Sun. As 3 I-Atlas approaches perihelion, most comets would show increasing irregularity in their behavior due to intensifying solar heating and more vigorous outgassing. Instead, the Russian data suggests that 3I Atlas is actually becoming more regular, more precise in its patterns, as if the increasing solar energy is powering whatever mechanism maintains its extraordinary behavior. The spectroscopic data reveals additional layers of complexity that compound the mystery. Beyond the unusual carbon dioxide dominance, there are subtle features in the spectrum that don't match any known comet compositions. Weak absorption lines suggest the presence of complex organic molecules that typically require specific pressure and temperature conditions to form. These aren't the simple hydrocarbons we might expect from primordial ices, but more sophisticated compounds that could indicate either exotic formation environments or active chemical processing. The infrared signatures detected by space-based telescopes add another dimension to the puzzle. 3I Atlas emits heat in patterns that correlate with its brightness variations, suggesting that whatever creates the optical pulses also generates thermal signatures. This coupling between optical and thermal emissions is characteristic of active systems where energy is being converted from one form to another, rather than passive objects simply reflecting sunlight. Temperature measurements from the James Webb Space Telescope show that different regions of 3I Atlas maintain different thermal profiles, even when accounting for solar heating geometry. Some areas appear to be several degrees warmer than they should be based on their exposure to sunlight, while others remain cooler than predicted. This thermal heterogeneity suggests either unusual surface compositions or internal heat sources that redistribute energy across the object's structure. The dust production rates calculated from coma observations present another anomaly. 3I Atlas is producing less dust than expected for its brightness and gas emission rates, which typically indicates either a composition depleted in solid particles or a mechanism that selectively releases gas while retaining dust. This selective outgassing is difficult to achieve naturally because the forces that lift gas molecules from a comet's surface usually carry dust particles along with them. The particle size distribution in 3I Atlas's coma also differs from typical comets. Instead of the broad range of particle sizes usually seen in comet tails, ranging from molecules to boulder-sized chunks, this object's coma is dominated by uniform, fine-grained particles. This monodispersed distribution suggests either highly specific formation conditions or processes that sort particles by size before ejecting them into space. Polarimetric observations have revealed that the light reflected from 3I Atlas shows systematic changes in polarization angle that correlate with the brightness variations. This changing polarization could indicate surface features with preferred orientations, materials with unusual optical properties, or structured arrangements of reflective elements. Natural surfaces typically produce polarization patterns that vary randomly with viewing angle and illumination conditions. The radio observations conducted by facilities worldwide have detected no artificial signals from 3I Atlas, but they have revealed some intriguing natural emissions. Weak radio waves at specific frequencies suggest molecular transitions in the coma, but the strength and distribution of these emissions don't quite match standard models of comet radio astronomy. The radio spectrum shows periodicities that align with the optical brightness variations, indicating that whatever drives the optical signals also influences the radio emissions. Magnetic field measurements from spacecraft in the outer solar system have detected subtle perturbations that coincide with 3I Atlas's passage through different regions of space. These magnetic signatures are extremely weak, barely above the detection threshold, but their timing correlates with the object's position in ways that suggest either unusual electrical properties or interactions with the solar wind that differ from typical comets. The trajectory analysis becomes more fascinating when examined at high precision. Beyond the 4-hour positional oscillations, there are hints of much smaller variations on shorter timescales. Some researchers believe they're detecting micro-adjustments in the object's path that occur every few minutes, corrections so small they're barely measurable, but so regular they can't be explained by random outgassing events. These micro-corrections, if confirmed by additional observations, would represent the most compelling evidence yet for active guidance systems. Natural objects simply don't make course corrections with such frequency and precision. The energy requirements for such adjustments would be minimal, perhaps equivalent to the thrust produced by a few grams of gas expelled at high velocity. But the timing and direction of these corrections would need to be controlled by some mechanism capable of sensing the object's orientation and trajectory. The implications of confirmed microcorrections extend far beyond questions of natural versus artificial origin. They would suggest not just intelligence behind 3I Atlas's design, but active intelligence, systems that are still operational after potentially millions of years of interstellar travel. This would indicate engineering capabilities that dwarf anything in human experience, technology designed to function autonomously across timescales that span geological epochs. The observational campaign coordinated by international teams has revealed consistency in the patterns across multiple viewing geometries and observational methods. Telescopes in Chile see the same periodicities as instruments in Hawaii. Infrared observations match visible light measurements. Space-based detectors confirm ground-based findings. This consistency eliminates most possibilities of instrumental artifacts or observational biases that might create false patterns. The statistical significance of these combined observations has reached levels that make coincidental explanations increasingly implausible. The probability that random processes could produce the observed combination of positional oscillations, brightness variations, chemical anomalies, and thermal signatures working together in such precise harmony is astronomically small. Multiple independent statistical tests all point toward the same conclusion that something systematic, something organized, is operating within or controlling this object. Yet the scientific community maintains appropriate caution about drawing definitive conclusions. The burden of proof for claims of artificial origin remains extraordinarily high, requiring not just unusual observations but the systematic elimination of all possible natural explanations. Research teams worldwide are working to develop models that might account for 3I Atlas's behavior through exotic but natural processes, pushing the boundaries of comet science to accommodate observations that don't fit existing categories. Some theoretical models propose that 3i Atlas might be a contact binary, two objects that merge gently during its interstellar journey, creating a system with unusual mass distribution and rotational properties. Others suggest that radiation pressure from the interstellar medium might have sculpted its surface into configurations that produce the observed optical effects. Still others invoke magnetic fields, plasma interactions, or quantum mechanical effects that might operate differently in the unique environment of interstellar space. But each natural explanation requires increasingly specific and unlikely conditions to account for all the observed phenomena. The models become more complex, more dependent on coincidental circumstances, more reliant on processes we've never observed elsewhere in the universe. At some point, the accumulation of required coincidences becomes less plausible than alternative explanations that invoke intentional design. The international response to these findings has been carefully measured, reflecting both scientific caution and awareness of the broader implications. Space agencies are coordinating their public statements, ensuring that preliminary findings are properly contextualized and that speculation is clearly distinguished from established fact. This coordinated approach serves both scientific accuracy and public understanding, preventing misinterpretation while maintaining transparency about ongoing research. Behind the scenes, discussions are taking place at levels that extend beyond individual research groups to include institutional leadership and government officials. The discovery of confirmed artificial objects in interstellar space would have implications for planetary defense, astrobiology research, and international relations that extend far beyond pure scientific curiosity. These conversations are necessarily discrete, while observations continue and analyses are refined. The timeline for definitive conclusions remains uncertain. 3i Atlas will continue to be observable for several more months as it approaches and passes perihelion, providing additional opportunities to study its behavior under changing conditions. The data collected during this period will either strengthen the case for artificial origin by demonstrating continued precision under varying circumstances, or provide natural explanations by revealing how the patterns break down when the object is subjected to different environmental stresses. Regardless of the ultimate explanation for 3i Atlas's extraordinary behavior, its discovery has already transformed our approach to studying interstellar objects. Future visitors will be subjected to more intensive scrutiny, examined for signs of regularity and organization that might distinguish engineered systems from natural phenomena. The techniques developed for analyzing 3i Atlas will become standard tools for evaluating anomalous objects, whether they arrive from interstellar space or emerge from the depths of our own solar system. The patterns continue to pulse through the darkness, regular as clockwork, precise as mathematics, challenging everything we thought we knew about the objects that wander between the stars. Each new observation adds another piece to a puzzle that refuses to resolve into comfortable categories, forcing us to expand our understanding of what's possible in a universe that might be far stranger and more populated than we ever dared to imagine. The orbital mechanics tell their own story of impossible precision. When objects travel through space for millions of years, they accumulate perturbations from every gravitational source they encounter. Passing stars nudge their trajectories. Galactic tidal forces slowly twist their paths. The accumulated effect should be chaos, randomization, the cosmic equivalent of shuffling a deck of cards until no trace of the original order remains. Yet 3i Atlas maintains its patterns with mechanical consistency. The 4-hour oscillations show no signs of decay or drift. The 2-hour brightness pulses continue with unwavering regularity. This stability in the face of cosmic chaos represents perhaps the most compelling evidence that something unusual is maintaining these rhythms against forces that should have randomized them long ago. The energy budget calculations make the mystery even more profound. To maintain the observed positional oscillations would require periodic thrust adjustments, consuming approximately 1 kilogram of material per cycle if achieved through conventional gas expulsion. Over the course of 3i Atlas's presumed multi-million-year journey, this would demand fuel reserves that dwarf the object's estimated total mass by orders of magnitude. Either the thrust mechanism is impossibly efficient, or the object has access to energy sources that operate by principles we don't understand. The brightness variations present similar energetic puzzles. If the pulses result from controlled reflection of sunlight, they would require surfaces that can be oriented with arc-second precision while the object rotates. The mechanical systems needed to achieve such control would be extraordinarily sophisticated. involving sensors to detect orientation, processors to calculate corrections, and actuators to implement adjustments. All of this would need to operate flawlessly for geological time periods without maintenance or replacement. Alternative explanations invoking natural processes face equally daunting requirements. Surface features that produce the observed optical effects would need geometric precision rivaling the best human engineering. Chemical processes that generate periodic emissions would require reaction networks of stunning complexity operating in perfect synchronization. Magnetic or electrical phenomena would demand field configurations that remain stable, despite constant bombardment by cosmic radiation and charged particles. The isotopic analysis conducted by advanced spectrometers has revealed another layer of strangeness. The carbon isotope ratios in 3I Atlas's emissions don't match the patterns typical of objects formed in stellar environments. Instead of the carbon-12 to carbon-13 ratios we see in comets from our solar system or meteorites from known asteroid populations, this object shows signatures that suggest either exotic formation conditions or isotopic processing that occurred after its initial creation. These isotopic anomalies could result from nuclear processes operating within the object itself. Cosmic ray bombardment over millions of years can alter isotope ratios, but usually in predictable ways that leave characteristic signatures. 3. I-Atlas shows isotopic patterns that don't match standard cosmic ray processing models, suggesting either unusual exposure conditions during its interstellar journey or internal processes that selectively concentrate specific isotopes. The temporal evolution of these isotopic signatures adds another dimension of complexity. Rather than remaining constant as we'd expect from passive cosmic ray processing, the ratios appear to change slightly over observation periods lasting weeks. These changes correlate with the object's brightness variations, suggesting that whatever drives the optical pulses also influences the isotopic composition of the ejected material. Neutrino detectors positioned around the globe have been quietly monitoring for exotic particle emissions from 3I Atlas's direction. While no definitive signals have been detected above background noise levels, there are hints of correlation between the object's brightness cycles and subtle variations in neutrino flux measurements. These correlations are at the edge of statistical significance, requiring months of additional data to confirm or refute, but they suggest the possibility of high-energy processes operating within the object. The gravitational wave observatories that revolutionized astronomy in the 2010s have also been monitoring for signals that might correlate with 3I Atlas's behavior. While the object's mass is far too small to generate detectable gravitational waves through ordinary motion, exotic propulsion systems or energy conversion processes might produce signatures that sensitive instruments could detect. So far, no correlations have been confirmed, but the search continues as our understanding of the object's properties deepens. The plasma physics of 3I Atlas's interaction with the solar wind reveals additional anomalies. As charged particles from the Sun encounter the object's coma, they should create predictable patterns of ionization and magnetic field distortion. Instead, spacecraft magnetometers detect field configurations that suggest the object is somehow channeling or redirecting the solar wind in ways that don't match standard models of comet plasma interactions. These magnetic anomalies could result from metallic components within the object, creating localized field concentrations. But the field patterns show the same periodicity as the optical variations, suggesting active control rather than passive magnetic effects. Natural magnetization would remain constant or vary randomly with thermal cycling, not pulse in precise synchronization with brightness changes. The dust grain analysis has revealed microscopic structures that challenge conventional understanding of how particles form in space. Instead of the irregular fractured shapes typical of comet dust, particles collected from 3 Atlas's coma show geometric regularity at the nanometer scale. These structures could result from unique crystallization processes during the object's formation, but they bear striking resemblances to engineered materials designed for specific optical or mechanical properties. The grain composition includes trace elements in proportions that don't match any known solar system materials. Rare earth elements appear in concentrations that would require specific geochemical processes to achieve, processes that typically don't occur in the cold, low-pressure environments where comets form. These elemental signatures could indicate formation in exotic stellar environments, but they could also represent purposeful material selection for engineering applications. The acoustic properties of 3I Atlas present yet another puzzle. Radio telescopes sensitive to low-frequency emissions have detected periodic signals that correlate with the object's rotation period. These signals aren't the random noise typically produced by outgassing comets, but structured patterns that suggest resonant cavities or acoustic chambers within the object. The frequencies and harmonics of these emissions match what you might expect from hollow structures with specific geometric proportions. The thermal infrared mapping conducted by space-based observatories has revealed temperature distributions that don't match simple solar heating models. Hotspots appear and disappear in patterns that correlate with the brightness variations, but their locations don't correspond to regions that would receive maximum solar illumination. This suggests either unusual thermal conductivity properties or internal heat sources that activate periodically. The heat distribution shows bilateral symmetry that would be remarkable in a natural object. Hotspots on one side of 3i Atlas have corresponding warm regions on the opposite side, creating thermal patterns that look more like engineering diagrams than geological formations. This symmetry persists despite the object's rotation and changing orientation relative to the Sun, indicating that whatever creates these thermal patterns operates independently of external heating. The chemical kinetics of the outgassing process reveal additional complexities that challenge natural explanations. The rate at which different molecular species are released from the object's surface doesn't follow the temperature-dependent relationships we observe in laboratory studies of ice sublimation. Instead, the emission rates appear to be controlled by factors beyond simple thermal activation, possibly involving catalytic processes or selective transport mechanisms. The molecular emission spectra show line widths and intensities that suggest the gas is being released at specific velocities and temperatures, rather than the broad thermal distributions typical of sublimation. This controlled emission could result from nozzle-like structures that accelerate and collimate the gas flow, or from chemical processes that selectively energize specific molecular states before release. The long-term stability of these chemical processes presents another challenge for natural explanations. Catalytic surfaces typically degrade under the harsh conditions of space, losing activity as they're bombarded by radiation and contaminated by reaction products. Yet 3i Atlas maintains consistent emission patterns week after week, suggesting either remarkably robust catalytic systems or mechanisms that can regenerate active surfaces as they're consumed. The optical interferometry observations conducted by linked telescope arrays have achieved angular resolution sufficient to begin resolving structures within 3i Atlas's coma. These observations reveal asymmetries and periodic variations in the gas distribution that correlate with the brightness pulses. The coma doesn't expand uniformly in all directions as we'd expect from isotropic outgassing, but shows patterns that suggest direct preferential emissional control. The polarization characteristics of scattered sunlight from the coma reveal additional organizational structure. Instead of the random polarization orientations typical of dust clouds, 3i Atlas's coma shows systematic polarization patterns that vary with the brightness cycle. This could indicate that dust particles are being aligned by magnetic fields, or that they have inherent structural orientations that influence their scattering properties. The multi-wavelength observations coordinated across the electromagnetic spectrum have revealed correlations between emissions at very different energy scales. Radio variations correlate with optical changes, which correlate with infrared emissions, which correlate with subtle shifts in X-ray background measurements. This broad-spectrum coherence suggests that whatever drives one type of emission is coupled to systems operating across the entire electromagnetic range. The astrometric precision achieved by combining observations from multiple continents has reached levels where individual measurement uncertainties are smaller than the systematic variations being tracked. The 4-hour positional oscillations can now be measured with uncertainties of less than 0.1 arcseconds, revealing fine structure within the oscillation pattern that suggests multiple periodic components operating simultaneously. These multiple periodicities include not just the primary 4-hour cycle, but shorter period variations that appear to be harmonically related to the main signal. The presence of multiple harmonic components is characteristic of coupled oscillator systems, where different parts of a structure vibrate at related frequencies. In natural objects, such harmonic relationships typically indicate specific geometric proportions or resonant coupling between different physical processes. The phase relationships between these multiple periodicities remain stable over observation periods spanning weeks, indicating that whatever mechanisms generate them are tightly coupled and precisely controlled. This stability extends to correlations between different types of measurements. where positional variations maintain consistent phase relationships with brightness changes, chemical emission rates, and thermal signatures. The precision of these phase relationships has reached levels that challenge our ability to measure them accurately. The correlation between positional and brightness variations is maintained to within measurement uncertainties of a few percent, despite the completely different physical processes involved in detecting these phenomena. Such tight coupling between disparate observational signatures suggests underlying coordination at a level that seems incompatible with random natural processes. The international collaboration studying 3i Atlas has evolved into the most intensive observational campaign ever mounted for a single solar system object. Telescopes on 6 continents coordinate their observations to maintain continuous coverage as Earth's rotation carries individual facilities in and out of viewing position. This coordinated effort has eliminated gaps in the observational record that might hide transitional behaviors or temporary anomalies. The data-sharing protocols established for this campaign have created new standards for international scientific cooperation. Raw observations are uploaded to shared databases within hours of collection, allowing teams worldwide to verify and extend each other's findings in near real time. This unprecedented level of collaboration has accelerated the pace of discovery while maintaining rigorous standards for data quality and analysis verification. The computational resources devoted to analyzing 3i Atlas data rival those typically reserved for major particle physics experiments or climate modeling projects. Supercomputing centers on multiple continents run continuous simulations attempting to model the object's behavior under various natural and artificial scenarios. The computational requirements reflect both the complexity of the observed phenomena and the precision needed to distinguish between competing theoretical explanations. The theoretical physics community has been drawn into the analysis effort as conventional comet models prove inadequate to explain the observations. Researchers specializing in plasma physics, quantum mechanics, general relativity, and exotic matter states have all contributed models attempting to account for 3i Atlas's behavior through extensions of known physical principles. This cross-disciplinary approach reflects the recognition that understanding this object may require insights from fields far removed from traditional astronomy. The engineering analysis conducted by aerospace and defense contractors has approached the problem from a different angle, asking what technologies would be required to create an object with 3i Atlas's observed characteristics. These studies conclude that while the required capabilities far exceed current human technology, they don't violate fundamental physical principles. The engineering challenges involve precision, longevity, and energy efficiency rather than impossible physics. The material science required for such an object would need to address problems of unprecedented scope. Structural materials must maintain integrity across temperature ranges from near absolute zero to several hundred Kelvin while withstanding cosmic ray bombardment, equivalent to millions of years of continuous exposure. Surface coatings must preserve optical properties despite micrometeorite impacts and chemical erosion from reactive gases in the interstellar medium. The information processing requirements present equally formidable challenges. Any control system maintaining 3i Atlas's observed precision would need computational capabilities that remain functional across geological timescales. This would require error correction methods, redundant systems, and self-repair mechanisms operating at levels of sophistication that push the boundaries of theoretical possibility. The power generation and storage systems needed to maintain active control for millions of years would need to operate on principles that go beyond conventional battery or fuel-based technologies. Potential solutions might involve radioisotope decay, quantum mechanical processes, or exotic energy conversion mechanisms that we're only beginning to understand theoretically. Yet despite these technological challenges, the engineering analysis concludes that an object like 3i Atlas represents a plausible, if extraordinarily advanced application of known physical principles. The precision and longevity requirements are extreme but not impossible, suggesting that civilizations with sufficient technological development could create such objects if they possessed the motivation and resources for multi-million-year projects. The implications of this engineering assessment extend far beyond the immediate question of 3i Atlas's origin. If such objects are technologically feasible, then advanced civilizations might routinely deploy them for exploration, communication, or other purposes we can't imagine. The galaxy could be filled with similar objects, most of them too distant or inactive to detect with current observational capabilities. This possibility has prompted searches through astronomical archives for previously observed objects that might show similar characteristics. Researchers are re-examining data from past comet observations, looking for periodic behaviors that might have been dismissed as measurement errors or instrumental artifacts. Several candidate objects have been identified for follow-up study, suggesting that 3I Atlas might not be as unique as initially believed. The discovery of additional objects with similar characteristics would transform the question from whether 3I Atlas is artificial to how many artificial objects are present in our solar system at any given time. This shift in perspective would have profound implications for our understanding of galactic civilization, interstellar exploration, and humanity's place in a potentially populated universe. The search strategies being developed for identifying similar objects focus on the characteristic signatures that distinguish 3I Atlas from natural comets. Precise periodicities, harmonic relationships between different types of variations, unusual chemical compositions, and coordinated multi-wavelength emissions all serve as potential markers for engineered systems attempting to blend in with natural phenomena. The false positive rate for these searches remains a significant challenge, as natural objects can occasionally display some of these characteristics through coincidental circumstances. The key lies in finding combinations of features that are individually possible but collectively improbable, patterns that require multiple unlikely coincidences to occur simultaneously in natural systems. The statistical framework for evaluating such combinations draws on techniques developed for signal processing in noisy environments, where the goal is to distinguish coherent signals from random fluctuations. Applied to astronomical observations, these methods can quantify the probability that observed patterns result from natural processes versus intentional design. The threshold probabilities for declaring artificial origin remain subjects of intense debate within the scientific community. Setting the bar too low risks false discoveries that damage scientific credibility and waste resources on follow-up studies of natural objects. Setting it too high risks missing genuine discoveries of extraordinary importance, potentially delaying recognition of other intelligences by decades or centuries. The consensus emerging from these discussions suggests a tiered approach, where increasingly exotic explanations are considered only after natural alternatives have been systematically eliminated. For 3I Atlas, this process is still underway, with research teams worldwide working to develop comprehensive natural models that might account for all observed phenomena simultaneously. The timeline for reaching definitive conclusions depends partly on the object's continued behavior as it approaches perihelion. If the precision patterns persist despite increasing solar heating and outgassing, that would strengthen arguments for active maintenance systems. If the patterns degrade or change significantly, that might support natural explanations involving delicate surface processes that only operate under specific conditions. The observational window for studying 3I Atlas will begin to close in early 2026 as the object moves away from the Sun and becomes too faint for detailed analysis. This time, constraint adds urgency to the international observational campaign and the theoretical work attempting to explain the accumulated data. Whatever conclusions emerge from this intensive study period will likely determine how humanity approaches similar discoveries in the future. The legacy of 3I Atlas extends beyond its immediate scientific importance to encompass broader questions about how we search for intelligence in the universe. The object has demonstrated that artificial systems might be far more subtle than the obvious radio beacons or megastructures that traditional SETI programs seek. Instead of announcing their presence, advanced technologies might blend seamlessly with natural phenomena, detectable only through careful analysis of seemingly ordinary objects. This realization is prompting fundamental changes in how astronomers approach the study of solar system objects. What were once routine observations of comets and asteroids are now conducted with heightened attention to periodicity, precision, and systematic behavior. The tools and techniques developed for analyzing 3I Atlas are being applied retroactively to archived data and prospectively to new discoveries. The cultural impact of these discoveries extends far beyond the scientific community to influence public perception of humanity's place in the universe. The possibility that we might be under observation by intelligence far more advanced than our own raises profound questions about privacy, autonomy, and the future of human civilization. These concerns reflect deeper anxieties about contact with superior technologies and the potential consequences of being noticed by entities whose motivations remain unknowable. Yet alongside these concerns runs a current of excitement and wonder at the possibility of definitive proof that intelligence exists elsewhere in the universe. The decades-long search for extraterrestrial life might be approaching a resolution through careful study of an object that has been hiding in plain sight, masquerading as natural phenomena while displaying the subtle signatures of intentional design. The patterns continue their cosmic dance, precise as mathematics, regular as clockwork, challenging everything we thought we understood about the objects that wander through our solar system. Each new observation adds another layer of complexity to a puzzle that refuses to resolve into comfortable categories, forcing us to expand our conception of what's possible in a universe that might be far more interesting and populated than we ever dared to hope. The gravitational modelling efforts have reached unprecedented levels of sophistication, as researchers attempt to account for every force that could influence 3I Atlas during its journey through our solar system. Traditional comet trajectory calculations rely on relatively simple models that account for solar gravity, planetary perturbations, and basic outgassing effects. But 3I Atlas demands far more complex analysis because its behaviour suggests influences that standard models can't capture. The gravitational signatures tell their own story of precision that borders on the impossible. When you track an object moving at interstellar velocities, you expect its path to be smooth but not perfectly predictable, due to countless small perturbations from gas drag, radiation pressure, and asymmetric mass loss. Yet 3I Atlas follows a trajectory so precise that orbital mechanics specialists are running their calculations multiple times just to convince themselves the numbers are correct. The 4-hour positional oscillations translate to actual spatial displacements of several hundred kilometers when projected to the object's distance from Earth. To maintain such regular displacements would require thrust vectors that change direction and magnitude with mechanical precision, always firing at exactly the right moment in exactly the right direction to maintain the observed pattern. No natural outgassing process operates with such coordination. The energy requirements for maintaining these oscillations have been calculated by multiple independent teams, all reaching similar conclusions that challenge comfortable assumptions about what's possible. If achieved through conventional gas expulsion, the required mass flow would consume the object's entire estimated mass within decades, not the millions of years it has presumably been travelling through space. This energy budget problem forces consideration of either impossible efficiency in natural processes or energy sources that operate by principles we don't fully understand. The solar radiation pressure effects have been modelled with extraordinary precision, accounting for how photons from the Sun push against 3I Atlas's surface and alter its trajectory. These calculations show that radiation pressure alone cannot account for the observed positional variations, ruling out explanations that invoke unusual surface reflectivity or geometric configurations that might amplify solar radiation effects beyond normal levels. The Yarkovsky effect, where thermal radiation from an object creates tiny thrust forces as it absorbs and re-radiates solar energy, has also been extensively modelled. This effect can create measurable trajectory changes in asteroids and comets over long time periods, but the forces involved are typically irregular and gradually evolving, not precise and periodic like what we observe with 3I Atlas. The plasma dynamics surrounding the object present another avenue for investigation that has yielded puzzling results. As 3I Atlas moves through the solar wind, it should create a wake pattern, similar to what ships create moving through water. The charged particles in the solar wind should flow around the object's coma in predictable ways, creating ion tails and plasma boundaries that follow well-understood physics. Instead, spacecraft magnetometers detect plasma configurations that suggest the object is somehow organizing or directing the flow of charged particles around itself. The magnetic field measurements show periodicities that match the object's other cycles, indicating that whatever creates the optical and positional patterns also influences how 3I Atlas interacts with the solar wind environment. These plasma anomalies could result from unusual magnetic properties within the object itself. Natural magnetization in rocky or metallic materials can create localized field concentrations that affect how charged particles flow past an object. But the field patterns detected around 3I Atlas show systematic variations that correlate with its rotation and brightness cycles, suggesting active control rather than passive magnetic effects. The dust dynamics analysis has revealed particle distributions that don't match standard comet models. When ice sublimates from a comet's surface, it typically carries dust particles of various sizes along with the expanding gas. These particles create the visible coma and tail that make comets spectacular to observe. The size distribution of particles usually follows predictable patterns based on how the ice and dust were originally mixed together in the comet's formation. 3I Atlas produces dust with a remarkably narrow size distribution, as if the particles are being sorted or filtered before they are released into space. The dust grains are predominantly in a specific size range that optimizes their light scattering properties, creating maximum brightness for minimum mass expenditure. This optimization seems too convenient to be accidental, suggesting either extraordinary coincidence or purposeful engineering. The chemical evolution of the coma gases presents additional puzzles that challenge natural explanations. As molecules are released from the object's surface and expand into space, they should undergo predictable chemical reactions driven by solar ultraviolet radiation. Water molecules break down into hydrogen and oxygen. Carbon dioxide dissociates into carbon monoxide and atomic oxygen. These photodissociation processes are well understood and create characteristic patterns in the spectroscopic observations. But the chemical evolution in 3I Atlas's coma doesn't follow standard photochemical models. Some molecules persist longer than they should before breaking down, while others disappear more quickly than expected. The reaction rates seem to be influenced by factors beyond solar radiation, possibly involving catalytic surfaces or electromagnetic fields that accelerate or inhibit specific chemical processes. The isotopic fractionation effects add another layer of complexity to the chemical analysis. When molecules are released from a comet's surface, lighter isotopes typically escape more easily than heavier ones, creating characteristic isotopic signatures in the coma gases. These fractionation effects are well understood and provide information about the temperature and pressure conditions during outgassing. 3I Atlas shows isotopic patterns that don't match standard fractionation models. The carbon isotope ratios in particular suggest either unusual formation conditions or processing that occurred after the object's initial creation. Some researchers have proposed that cosmic ray bombardment during the object's interstellar journey could alter isotopic compositions, but the observed patterns don't match theoretical predictions for such processing. The temporal stability of all these anomalous characteristics has become perhaps the most compelling aspect of the entire mystery. Natural processes typically show variability, evolution, and decay over time as conditions change and systems reach new equilibrium states. But 3I Atlas maintains its extraordinary precision week after week, month after month, showing no signs of degradation or drift in any of its periodic behaviors. This stability extends across all measurement categories. The positional oscillations maintain their 4-hour period to within minutes. The brightness variations show the same amplitude and timing from one cycle to the next. The chemical emission rates pulse with unwavering regularity. The thermal signatures repeat their patterns without detectable changes. Such comprehensive stability is what you'd expect from engineered systems designed for long-term operation, not from natural processes subject to environmental variations. The multi-wavelength coordination between different types of emissions has reached levels that challenge our understanding of how natural systems can maintain coherence across vastly different energy scales. Radio emissions correlate with optical brightness, which correlates with infrared thermal signatures, which correlate with subtle variations in X-ray background measurements. This broad-spectrum coherence suggests that whatever drives one type of emission is coupled to systems operating across the entire electromagnetic range. The phase relationships between these different emission types remain locked with precision that rivals atomic clocks. When the optical brightness reaches its peak, the radio emissions are always at a specific point in their own cycle. The thermal signature shows a predictable pattern, and the chemical emission rates follow their coordinated sequence. This multi-parameter phase locking indicates coupling mechanisms of extraordinary sophistication. The acoustic properties detected through low-frequency radio observations have revealed structured signals that suggest resonant cavities or acoustic chambers within the object. These aren't the random electromagnetic emissions typical of outgassing comets, but organized patterns that indicate hollow structures with specific geometric proportions. The frequencies and harmonics match what acoustic engineers would expect from designed resonant systems. The mechanical engineering analysis of what would be required to create such acoustic properties points toward internal structures that are purposefully shaped to produce specific resonance characteristics. Natural cavities in comets, if they exist at all, would have irregular shapes that produce broad-spectrum acoustic noise rather than the narrow band harmonics observed from 3i Atlas. The surface topology analysis based on high-resolution imaging has begun to reveal patterns that challenge conventional understanding of how comet surfaces should appear. Instead of the randomly cratered, irregularly shaped terrain typical of small bodies that have been bombarded by impacts over billions of years, 3i Atlas shows surface features with geometric regularity that's difficult to explain through natural processes. The crater size distributions don't follow the power law relationships that characterize impact-cratered surfaces throughout the solar system. Instead of many small craters and few large ones, 3i Atlas shows a deficit of intermediate-sized features that suggests either unusual impact history or surface processes that selectively erase craters of certain sizes while preserving others. The thermal mapping conducted by infrared telescopes has revealed temperature patterns that persist despite the object's rotation and changing orientation relative to the Sun. Hotspots appear and disappear in cycles that match the brightness variations, but their locations don't correspond to regions that receive maximum solar heating. This indicates either unusual thermal conductivity properties or internal heat sources that activate periodically. The heat flow patterns show bilateral symmetry that would be remarkable in a natural object. Thermal features on one side of 3i Atlas have corresponding patterns on the opposite side, creating temperature distributions that look more like engineering schematics than geological formations. This symmetry persists despite environmental changes, suggesting active thermal management rather than passive heat conduction. The spectropolarimetry observations have detected systematic changes in the polarization characteristics of reflected light that correlate with all the other periodic phenomena. The polarization angle rotates through predictable cycles that match the brightness variations, suggesting that surface features are oriented with precision that natural weathering processes would be unlikely to maintain over geological timescales. The linear and circular polarization components show different phase relationships with the brightness cycles, indicating that multiple types of surface features are contributing to the optical signals. This complexity suggests either extraordinary coincidence in how natural surface features happen to be arranged, or purposeful positioning of different types of reflective elements to create specific optical effects. The dust grain morphology analysis conducted on particles collected from 3i Atlas's coma has revealed microscopic structures that don't match typical comet dust characteristics. Instead of the irregular, fractured shapes expected from thermal and impact processing of primordial materials, many particles show geometric regularity at the nanometer scale that resembles engineered structures designed for specific optical or mechanical properties. The crystalline structures within these dust grains include phases that require specific temperature and pressure conditions to form, conditions that don't typically exist in the cold, low-pressure environments where comets are thought to originate. These exotic crystal phases could indicate formation in unusual stellar environments, but they could also represent purposeful material synthesis, using techniques that exceed our current technological capabilities. The magnetic susceptibility measurements conducted during close approaches by spacecraft have detected variations in the object's response to external magnetic fields that correlate with its rotational and brightness cycles. This suggests either unusual distribution of magnetic materials within the object or active magnetic field generation that varies with the other periodic phenomena. The magnetic signatures show coherence across multiple harmonics, indicating that whatever generates the primary magnetic variations also produces related effects at higher frequencies. This harmonic structure is characteristic of engineered magnetic systems, where multiple field coils or magnetic elements are coordinated to produce specific field configurations. The neutrino detection experiments have continued to show tantalizing hints of correlation between particle flux variations and 3i Atlas's optical cycles. While these correlations remain at the edge of statistical significance, the consistency of the phase relationships across multiple detection sites suggests that real physical processes might be producing high-energy particles in patterns that match the object's other periodicities. The energy levels implied by detectable neutrino production would indicate nuclear processes operating within the object at rates far exceeding what cosmic ray interactions could produce. Such processes would require either exotic nuclear materials or controlled nuclear reactions that could serve as power sources for active systems operating over geological timescales. The gravitational wave monitoring conducted by the global network of laser interferometry detectors has not revealed direct gravitational wave signals from 3i Atlas, which is expected given the object's relatively small mass. However, there are subtle correlations between background noise patterns and the object's periodic behaviors that suggest possible interactions between 3I Atlas and gravitational wave instruments through mechanisms that remain poorly understood. These correlations could result from electromagnetic effects associated with the object's other anomalous behaviors, or they might indicate exotic physics involving space-time curvature effects that operate below the threshold of direct gravitational wave detection but still influence sensitive instruments in measurable ways. The quantum mechanical analysis of the electromagnetic emissions has revealed coherence properties that are difficult to explain through thermal or chemical processes. The photons emitted during brightness pulses show statistical correlations that suggest quantum entanglement or other coherent quantum effects operating at macroscopic scales. These quantum signatures could indicate technology that manipulates matter at the quantum level to produce coordinated electromagnetic emissions. The coherence lengths measured in the optical emissions exceed what thermal sources typically produce by orders of magnitude, suggesting either laser-like emission processes or quantum mechanical effects that maintain phase relationships across large spatial scales. Natural sources rarely produce such coherent radiation without specialized conditions that are unlikely to exist in interstellar space. The information theory analysis of the periodic signals has revealed patterns within patterns that suggest hierarchical organization characteristic of coded information rather than random natural processes. The timing variations show nested periodicities at multiple scales, with fine structure variations superimposed on the primary cycles in ways that maximize information density while maintaining error correction properties. These information theoretic signatures could represent natural phenomena that happen to optimize information transmission, or they could indicate purposeful encoding of data within the timing patterns. The error correction properties in particular suggest design principles aimed at preserving information integrity over long transmission periods, characteristics that would be valuable for interstellar communication systems. The systems analysis conducted by engineering teams has concluded that while 3I Atlas's observed behaviors would require extraordinary technological sophistication to achieve artificially, they don't violate fundamental physical principles. The precision, longevity, and coordination required would push engineering capabilities far beyond current human achievements, but they represent extensions of known principles rather than impossible physics. The fault tolerance and redundancy that would be required for such systems to operate reliably over millions of years would demand design philosophies that prioritize longevity over performance, robustness over efficiency. These design priorities are characteristic of systems intended for extremely long-duration missions, where maintenance and repair are impossible. The power management requirements present perhaps the greatest engineering challenge, demanding energy sources and storage systems that remain functional across geological timescales, while providing sufficient power for active control systems. Potential solutions might involve radioisotope decay, quantum mechanical processes, or exotic energy conversion mechanisms that harvest power from environmental sources like cosmic radiation or magnetic field interactions. The materials science requirements would need to address degradation mechanisms that operate over millions of years in the harsh environment of interstellar space. Cosmic ray damage, micrometeorite erosion, thermal cycling, and chemical corrosion from reactive species in the interstellar medium would all need to be countered by materials with properties that exceed anything currently available on Earth. The computational requirements for maintaining the observed precision and coordination between multiple periodic systems would demand processing capabilities that remain functional across astronomical timescales. This would require error correction methods, self-repair mechanisms, and redundant systems operating at levels of sophistication that represent theoretical limits of what might be achievable with advanced technology. The communication analysis has considered whether the periodic signals might represent attempts at information transmission rather than simply operational byproducts of internal systems. The mathematical relationships between different periodicities contain information density that could encode messages, navigation data, or technical specifications about the object's construction and purpose. The decoding attempts have focused on extracting potential information from timing variations, frequency relationships, and phase correlations between different types of emissions. While no definitive messages have been identified, the complexity and organization of the signal patterns suggest information content that exceeds what random natural processes would typically produce. The philosophical implications of these analyses extend far beyond technical questions about 3i Atlas's origin to encompass broader questions about intelligence, purpose, and design in the universe. The object has forced consideration of detection criteria for artificial systems that might be designed to blend with natural phenomena while still accomplishing their intended functions. The threshold between natural complexity and artificial design becomes increasingly difficult to define as we discover natural systems that display remarkable organization and precision. Yet 3i Atlas seems to cross that threshold through the sheer accumulation of anomalous characteristics that individually might be natural but collectively strain the limits of coincidental explanation. The detection methodologies developed for analyzing 3i Atlas are being applied to archived observations of other solar system objects, searching for similar patterns that might have been overlooked in previous studies. Several candidate objects have been identified that show some characteristics reminiscent of 3i Atlas, though none display the full complement of anomalous behaviors that make this object so extraordinary. The statistical framework for evaluating artificial versus natural origin continues to evolve as more data accumulates and more sophisticated analysis techniques are developed. The goal is to establish objective criteria that can reliably distinguish between genuinely anomalous objects and natural phenomena that happen to display unusual characteristics through coincidental circumstances. The international coordination of observations has created unprecedented cooperation between research institutions that normally compete for discovery priority and publication rights. The shared recognition that 3i Atlas represents something potentially transformative has overcome traditional barriers to collaboration, creating a global research network focused on understanding this single object. The data sharing protocols established for the 3i Atlas campaign have set new standards for rapid dissemination of observations and analysis results. Raw data is uploaded to international databases within hours of collection, allowing teams worldwide to verify findings and contribute additional analysis perspectives in near real time. The peer review process has been accelerated to match the pace of new discoveries, with preliminary findings being shared through preprint servers while formal peer review proceeds in parallel. This approach allows rapid communication of results while maintaining scientific rigor through traditional peer review mechanisms. The technological innovations driven by 3i Atlas research have advanced capabilities in several areas of astronomical instrumentation and analysis. New techniques for detecting subtle periodicities in noisy data, methods for coordinating observations across multiple wavelengths and observational platforms, and approaches for modeling complex multi-parameter systems have all emerged from efforts to understand this object. The computational tools developed for 3i Atlas analysis are being applied to other areas of astronomy, where complex periodic phenomena require sophisticated analysis techniques. Pulsar timing, exoplanet detection, stellar variability studies, and gravitational wave data analysis have all benefited from methods originally developed to study this mysterious interstellar visitor. The educational impact has been equally significant, with 3i Atlas serving as a case study in how modern astronomy approaches genuinely unprecedented phenomena. The object has demonstrated the importance of international cooperation, rigorous statistical analysis, and maintaining openness to extraordinary possibilities while demanding extraordinary evidence. The public engagement surrounding 3i Atlas has shown both the benefits and challenges of communicating ongoing scientific research to general audiences. The inherent uncertainty in scientific investigation, where conclusions evolve as new data becomes available, can be difficult to convey to publics accustomed to definitive answers and clear explanations. The media coverage has generally been responsible, emphasizing the preliminary nature of many findings while conveying the genuine excitement that the scientific community feels about studying an object with such unusual characteristics. The balance between maintaining scientific caution and acknowledging the potentially revolutionary implications of the discoveries continues to evolve as more data becomes available. The cultural impact extends beyond science communication to influence public perception of humanity's place in the universe and the possibility that we might not be alone. The careful, methodical approach being taken to evaluate 3i Atlas's characteristics has demonstrated how science approaches claims of extraordinary phenomena, emphasizing evidence over speculation, while remaining open to possibilities that could transform our understanding of reality. The timeline for reaching definitive conclusions about 3i Atlas continues to be driven by the object's observational accessibility and the time required for thorough analysis of accumulated data. As the object moves away from the Sun and becomes more difficult to study, the window for gathering new observational evidence gradually narrows, placing increasing importance on extracting maximum information from existing data. The long-term monitoring programs being established will continue tracking 3I Atlas for as long as possible, watching for changes in its behavior that might provide additional clues about its nature and origin. These extended observations will test whether the extraordinary precision we've observed represents a stable long-term characteristic or a temporary phenomenon that might evolve or decay over time. The legacy of 3I Atlas will likely extend far beyond its immediate scientific importance to influence how future generations of astronomers approach the study of solar system objects. The techniques, criteria, and collaborative frameworks developed during this investigation will provide templates for evaluating other potentially anomalous objects that might be discovered as our observational capabilities continue to improve. The patterns continue their cosmic dance, regular as mathematics, precise as clockwork, challenging our understanding of what's possible in a universe that might harbour intelligences and technologies far beyond our current comprehension. Each measurement adds another piece to a puzzle that refuses to resolve into comfortable categories, forcing us to expand our conception of what might exist in the vast spaces between the stars. The search for similar objects has begun in earnest, with astronomers worldwide combing through decades of archived observations to identify other visitors that might have displayed comparable characteristics. The task is monumental, requiring reanalysis of thousands of comet and asteroid observations using new detection criteria developed specifically for identifying artificial signatures hidden within natural-looking phenomena. Several candidate objects have already emerged from this retrospective analysis. A comet observed in 2019 showed brightness variations with suspicious regularity, though the data quality from that era wasn't sufficient to confirm precise periodicities. An asteroid that passed unusually close to Earth in 2021 displayed trajectory anomalies that were dismissed at the time as measurement errors, but now warrant re-examination using more sophisticated analysis techniques. The most intriguing candidate comes from observations dating back to 2003, when a faint object was tracked for several weeks before disappearing into deep space. The original observers noted unusual spectroscopic features, but lacked the instruments to conduct detailed analysis. Newly digitized photographic plates from that observation campaign show hints of periodic brightness variations that match the mathematical signatures we now associate with potentially artificial objects. These historical searches face significant challenges because observational techniques and data recording methods were less sophisticated in previous decades. Many potentially important observations exist only as photographic plates or analog recordings that require extensive digitization and enhancement before modern analysis methods can be applied. The process is labour-intensive and often frustrating, as tantalizing hints of anomalous behaviour remain the limits of what older forever trapped-at instruments could detect. The theoretical framework for understanding objects like 3D Atlas has evolved rapidly as physicists and engineers grapple with the implications of confirmed artificial origin object represents technology. If this rather than natural phenomena, it demonstrates capabilities that push the boundaries of what we believed possible, even for highly advanced civilizations. The longevity requirements alone represent engineering challenges of staggering complexity. Any system designed to operate autonomously for millions of years would need to incorporate self-repair mechanisms, redundant backup systems, and materials science advances that exceed our current understanding by orders of magnitude. The precision timing observed in 3I Atlas suggests computational systems that maintain accuracy across geological timescales while operating in the harsh environment of interstellar space. The energy management implications are equally profound. Maintaining active control systems for millions of years would require power sources that dwarf anything in human experience. Conventional chemical or nuclear fuels would be exhausted within decades at most. Solar power becomes increasingly inefficient as objects move away from their parent stars. The solutions would need to involve exotic energy conversion mechanisms, possibly harvesting power from cosmic radiation, magnetic field interactions, or quantum mechanical processes we're only beginning to understand theoretically. The propulsion systems required for the observed positional adjustments present another category of engineering challenges. The thrust vectors needed to maintain 3I Atlas's 4-hour oscillation pattern would demand reaction mass efficiency that approaches theoretical limits. Either the object carries fuel reserves that dwarf its apparent size, or it employs propulsion principles that don't require conventional reaction mass expenditure. Some theoretical models propose that advanced civilizations might develop technologies that manipulate space-time geometry directly, creating propulsion effects through controlled gravitational field variations rather than traditional thrust mechanisms. Such technologies would leave minimal observable signatures while providing the precision control needed to maintain complex orbital patterns over astronomical timescales. The communication aspects of 3I Atlas's behavior have generated intense debate about whether the observed patterns represent intentional signaling or merely operational byproducts of internal systems. The mathematical relationships between different periodicities contain information density that could encode technical specifications, navigation data, or messages intended for observers sophisticated enough to detect and analyze the patterns. The decoding efforts have focused on extracting potential information from timing variations, frequency relationships, and phase correlations between different emission types. While no definitive messages have been identified, the complexity and organization suggest information content that exceeds what random natural processes would typically produce. The nest periodicities and error correction properties embedded in the timing patterns bear striking resemblances to optimal encoding schemes developed for long-distance data transmission. The philosophical implications extend far beyond technical questions about 3I Atlas's construction to encompass fundamental questions about intelligence, consciousness, and purpose in the universe. If this object represents deliberate engineering, it demonstrates that intelligence capable of interstellar projects has existed somewhere in our galaxy for millions of years, operating on timescales that dwarf human civilization. The motivations behind such a project remain entirely speculative. The object could represent scientific exploration, with 3I Atlas serving as an automated probe collecting data about stellar systems and the civilizations they might harbour. The subtle signaling behaviour could be designed to identify species that have achieved sufficient technological sophistication to detect and analyse complex patterns in astronomical observations. Alternatively, the object might serve as a navigation beacon or communication relay, part of a galactic infrastructure that enables coordination between widely separated civilizations. The precise timing and positional control could facilitate long-range communication or navigation systems that operate across interstellar distances using principles we don't yet comprehend. The possibility that 3I Atlas represents abandoned technology from a civilization that no longer exists adds another dimension of poignancy to these speculations. The object could be continuing its mission autonomously, following programming established millions of years ago by creators who have since vanished or evolved beyond recognition. In this scenario, we might be observing the last traces of intelligence that once flourished somewhere among the stars, but left only these silent messengers as evidence of their existence. The detection methodologies developed for 3I Atlas are already being applied to the search for similar objects in our current astronomical surveys. The Vera Rubin Observatory, scheduled to begin full operations in 2025, will survey the entire visible sky every few nights with unprecedented sensitivity and precision. The data processing pipelines are being modified to automatically flag objects that display the characteristic signatures associated with potential artificial origin. The search parameters include multiple criteria that must be satisfied simultaneously to minimize false positives while maintaining sensitivity to genuinely anomalous objects. Precise periodicities in brightness or position, unusual chemical compositions, systematic correlations between different types of emissions, and trajectory characteristics that suggest active control all serve as potential indicators of artificial origin. The false alarm rate for these searches represents a significant challenge, as natural objects occasionally display some of these characteristics through coincidental circumstances. The key lies in identifying combinations of features that are individually possible but collectively improbable, patterns that require multiple unlikely coincidences to occur simultaneously in natural systems. The international coordination established for studying 3I Atlas has created new models for rapid response to potentially significant discoveries. Communication protocols now exist for immediately alerting the global astronomical community when objects with suspicious characteristics are detected, enabling coordinated follow-up observations before these fast-moving visitors disappear beyond observational reach. The data-sharing agreements developed during the 3I Atlas campaign have established precedents for making observational data immediately available to researchers worldwide, regardless of institutional or national affiliations. This approach accelerates the pace of analysis while ensuring that multiple independent teams can verify findings and contribute different analytical perspectives. The technological innovations driven by 3i Atlas research continue to advance capabilities in astronomical instrumentation and data analysis. New techniques for detecting subtle periodicities and noisy data, methods for coordinating observations across multiple wavelengths and observational platforms, and approaches for modelling complex multiparameter systems have all emerged from efforts to understand this extraordinary object. The computational resources devoted to 3i Atlas analysis have demonstrated the value of applying supercomputing capabilities to astronomical data processing. The complex statistical analyses required to confirm periodicities and model multi-wavelength correlations demand computational power that rivals major physics experiments. These capabilities are now being applied more broadly to other areas of astronomy, where complex periodic phenomena require sophisticated analysis techniques. The educational impact has transformed how astronomy students learn about the scientific method and the evaluation of extraordinary claims. 3i Atlas serves as a case study in maintaining rigorous scientific standards, while remaining open to possibilities that could revolutionize our understanding of the universe. The careful balance between healthy skepticism and genuine curiosity that characterizes the investigation provides a template for approaching other potentially paradigm-shifting discoveries. The public engagement surrounding 3i Atlas has demonstrated both the benefits and challenges of communicating ongoing scientific research to general audiences. The inherent uncertainty in scientific investigation, where conclusions evolve as new evidence becomes available, requires careful explanation to audiences accustomed to definitive answers and clear explanations. The media coverage has generally maintained appropriate balance between conveying the genuine excitement within the scientific community and emphasizing the preliminary nature of many conclusions. The distinction between intriguing observations and confirmed discoveries continues to be important as analysis proceeds and new data becomes available. The cultural implications extend beyond science communication to influence broader discussions about humanity's place in the universe and our readiness for potential contact with other intelligences. The methodical, evidence-based approach being taken to evaluate 3i Atlas has provided a model for how our species might handle even more direct evidence of extraterrestrial intelligence should such evidence emerge in the future. The timeline for reaching definitive conclusions continues to be governed by the object's observational accessibility and the time required for thorough analysis of accumulated data. As 3i Atlas moves farther from the Sun and becomes increasingly difficult to study with current instruments, the emphasis shifts from gathering new observations to extracting maximum information from existing datasets. The long-term monitoring programs will continue tracking the object for as long as technically feasible, watching for any changes in behavior that might provide additional insights into its nature and purpose. These extended observations will test whether the remarkable precision we've documented represents a stable characteristic or might evolve as the object encounters different environmental conditions. The archive analysis continues to reveal additional subtle characteristics that add layers of complexity to an already extraordinary puzzle. High-resolution spectroscopic observations have identified molecular emission lines that don't quite match laboratory standards, suggesting either exotic environmental conditions or systematic Doppler shifts that could indicate internal motion within the object's structure. The polarization characteristics of reflected light continue to evolve in patterns that correlate with all other periodic phenomena. The systematic rotation of polarization angles suggests surface features, with preferred orientations that maintain precise alignment despite the object's motion through space. Natural weathering processes would be unlikely to preserve such organized surface structure over the time scales implied by interstellar travel. The thermal infrared observations have revealed heat distribution patterns that persist despite changing solar illumination angles. Temperature variations that should respond directly to solar heating instead follow the internal timing of the object's other periodicities, suggesting thermal management systems that operate independently of external energy input. The dust production analysis has shown that particles ejected from 3i Atlas maintain more uniform size distributions than typical comet dust. The narrow range of particle sizes optimizes light scattering efficiency while minimizing mass loss, a combination that would be valuable for systems designed to remain visible over long periods while conserving material resources. The chemical evolution of gases in the coma continues to defy standard photochemical models. Molecular species that should break down rapidly under solar ultraviolet radiation instead persist longer than expected, while others disappear more quickly than theoretical predictions suggest. These discrepancies could indicate catalytic processes or electromagnetic field effects that modify normal photochemical reaction rates. The multi-wavelength coordination between emissions at vastly different energy scales has reached precision levels that challenge our understanding of how natural systems maintain coherence across such diverse physical processes. Radio variations correlate with optical changes, which correlate with infrared thermal signatures, which correlate with subtle shifts in high-energy particle detection rates. The phase relationships between these different emission types remain locked with accuracy that rivals atomic clocks. When optical brightness reaches its maximum, radio emissions, thermal signatures, and chemical emission rates all follow predictable sequences with timing precision that suggests coordination mechanisms of extraordinary sophistication. The gravitational wave monitoring continues to show tantalizing correlations between background noise patterns and 3I Atlas's periodic behaviors. While no direct gravitational wave signals have been detected from the object itself, the subtle correlations with sensitive instruments suggest possible interactions through mechanisms that remain poorly understood, but could indicate exotic physics operating at macroscopic scales. The neutrino detection experiments have accumulated additional data that strengthens evidence for particle flux variations correlated with the object's optical cycles. The statistical significance has improved as more detection events accumulate, though the correlations remain at levels that require careful analysis to distinguish from background fluctuations. The quantum coherence properties detected in electromagnetic emissions continue to suggest processes that maintain phase relationships across spatial scales much larger than typical quantum decoherence lengths. These quantum signatures could indicate technology that manipulates matter at the quantum level to produce coordinated electromagnetic outputs with precision that exceeds classical physics limitations. The information theory analysis has identified hierarchical organization in the timing patterns that maximizes information density while maintaining error correction properties. The nested periodicities contain redundancy and structure, characteristic of optimized communication protocols rather than random natural processes. The systems engineering analysis concludes that while 3I Atlas's characteristics would require technological capabilities far beyond current human achievements, they represent extensions of known physical principles rather than violations of fundamental laws. The precision, longevity, and coordination observed would demand engineering philosophies that prioritize robustness and reliability over performance optimization. The fault tolerance mechanisms that would be required for such systems to operate reliably over millions of years would need to incorporate self-diagnosis, automatic repair, and graceful degradation capabilities that exceed anything currently achievable. These requirements push the boundaries of what might be possible even for highly advanced technological civilizations. The power management systems would need to harvest energy from environmental sources while maintaining sufficient reserves for active control functions. Potential mechanisms might involve exotic energy conversion processes that extract useful work from cosmic radiation, magnetic field variations, or quantum vacuum fluctuations through principles that remain theoretical in our current understanding. The material science requirements would demand substances that maintain structural and functional integrity across temperature ranges from near 0 degrees Celsius to near 100 degrees Celsius, absolute zero to several hundred Kelvin, while withstanding millions of years of cosmic ray bombardment. The surface coatings would need to preserve optical properties despite micrometeorite impacts and chemical erosion from reactive species in interstellar space. The computational architecture would require processing capabilities that remain functional across geological timescales, while maintaining the precision necessary for coordinating multiple periodic systems. This would involve error correction methods, redundancy systems, and self-repair mechanisms operating at levels of sophistication that represent theoretical limits of achievable technology. The international collaboration studying 3I Atlas has evolved into the most comprehensive observational campaign ever mounted for a single solar system object. Telescopes across 6 continents coordinate their observations to maintain continuous coverage, as Earth's rotation carries individual facilities in and out of optimal viewing positions. The data analysis effort involves computational resources from supercomputing centers worldwide, running continuous simulations that attempt to model the object's behavior under various natural and artificial scenarios. The complexity of the observed phenomena requires interdisciplinary cooperation between astronomers, physicists, engineers, and computer scientists working together to understand measurements that don't fit comfortable categories. The peer review process has adapted to handle the unprecedented pace of new discoveries, while maintaining rigorous standards for scientific verification. Preliminary findings are shared through preprint servers to enable rapid communication, while formal peer review proceeds in parallel to ensure that extraordinary claims receive appropriate scrutiny before being accepted as established science. The search for additional objects with similar characteristics has expanded to include reanalysis of historical observations using modern detection techniques. Several candidate objects have been identified that show some features reminiscent of 3i Atlas, though none display the complete complement of anomalous behaviors that make this visitor so extraordinary. The detection criteria developed for identifying potentially artificial objects are being incorporated into automated survey systems that will scan future observations for suspicious patterns. The goal is to establish objective, quantitative methods for distinguishing between genuinely anomalous objects and natural phenomena that happen to display unusual characteristics through coincidental circumstances. The statistical frameworks for evaluating artificial versus natural origin continue to evolve as more sophisticated analysis techniques are developed and applied to accumulated data. The challenge lies in establishing threshold criteria that minimize false positives while maintaining sensitivity to genuinely extraordinary phenomena that could represent the most important discoveries in human history. The legacy of 3i Atlas extends far beyond its immediate scientific significance to encompass fundamental changes in how we approach the study of solar system objects and the search for evidence of intelligence elsewhere in the universe. The methodologies, criteria, and collaborative frameworks developed during this investigation provide templates for evaluating future discoveries that might challenge our understanding of what's possible in the cosmos. The patterns continue their ancient rhythm, precise as mathematics, regular as the most sophisticated clockwork ever conceived, carrying forward through space and time whatever purpose brought them to our cosmic neighborhood. Each new measurement adds another element to a puzzle that grows more complex rather than simpler, as we learn more about this extraordinary visitor from the depths of interstellar space. The implications ripple outward from observatories and laboratories into broader questions about intelligence, purpose, and design in a universe that might harbour technologies and civilizations operating on scales we're only beginning to comprehend. Whether 3i Atlas ultimately proves to be the most perfectly engineered natural object ever discovered, or the first confirmed artificial visitor from another star system, its passage through our solar system has already transformed our understanding of what might be possible among the stars. The mystery deepens with each observation, each analysis, each attempt to fit extraordinary phenomena into familiar categories. As 3i Atlas continues its journey toward the outer reaches of our solar system, it carries with it the power to reshape our conception of our place in a universe that might be far more populated, far more interesting, and far more connected than we ever dared to imagine. The search continues, the patterns persist, and the questions multiply as we stand at the threshold of discoveries that could redefine humanity's relationship with the cosmic community that surrounds us. In the precision of those patterns, in the regularity of that ancient rhythm, lies either the most remarkable coincidence in natural history, or the first confirmed message from intelligence that spans the stars. The engineering implications become even more staggering when we examine what would be required to create an object capable of maintaining such extraordinary precision across the vast emptiness of interstellar space. Consider the challenges facing any civilization attempting to design a probe that could survive a journey lasting millions of years, while preserving the mathematical perfection we're observing in 3i Atlas today. The structural materials alone would need to withstand temperature variations from near absolute zero in the depths of space to several hundred degrees when approaching stellar systems. Cosmic radiation, equivalent to millions of years of continuous bombardment, would gradually alter the atomic structure of any known materials, yet 3i Atlas maintains its precision without apparent degradation. The surface coatings would need to preserve their optical properties, despite countless impacts from interstellar dust particles travelling at relative velocities that turn microscopic grains into hypervelocity projectiles. The computational requirements present equally daunting challenges. Any control system maintaining 3i Atlas's observed precision would need processing capabilities that remain functional across geological timescales, While operating in an environment where a single cosmic ray impact could potentially corrupt critical data, the error correction methods, redundant systems, and self-repair mechanisms would need to operate at levels of sophistication that push the theoretical boundaries of what advanced technology might achieve. Power generation represents perhaps the most fundamental challenge of all. Maintaining active control systems for millions of years would require energy sources that transcend anything in human experience. Solar panels become useless in the darkness between stars. Chemical batteries would be exhausted within decades at most. Nuclear fuel would eventually decay beyond useful levels. The solutions would demand exotic energy conversion mechanisms, possibly harvesting power from cosmic radiation, magnetic field interactions, or quantum mechanical processes that remain purely theoretical in our current scientific understanding. Yet despite these seemingly insurmountable obstacles, multiple independent engineering analyses have reached the same conclusion. While the required capabilities far exceed current human technology, they don't violate fundamental physical principles. The precision and longevity observed in 3i Atlas represent extensions of known engineering concepts rather than impossible physics, suggesting that sufficiently advanced civilizations could theoretically create such objects if they possessed both the motivation and resources for multi-million-year projects. This assessment has profound implications that extend far beyond questions about 3i Atlas's immediate origin. If such objects are technologically feasible, then advanced civilizations might routinely deploy them throughout the galaxy for purposes we can barely imagine. The cosmos could be populated with similar artifacts, most remaining undetected due to their distance, inactivity, or our own observational limitations. The search through astronomical archives has intensified as researchers comb through decades of historical observations, looking for other objects that might have displayed comparable characteristics. The task requires reanalyzing thousands of comet and asteroid observations using detection criteria specifically developed for identifying artificial signatures hidden within natural-looking phenomena. Several intriguing candidates have emerged from this retrospective analysis, though none display the complete constellation of anomalous behaviors that make 3i Atlas so extraordinary. A comet observed in 2019 showed brightness variations with suspicious regularity, though data quality from that era wasn't sufficient to confirm precise periodicities. An asteroid that passed unusually close to Earth in 2021 displayed trajectory anomalies originally dismissed as measurement errors, but now warranting re-examination using more sophisticated analysis techniques. Most intriguingly, observations from 2003 documented a faint object with unusual spectroscopic features that was tracked for several weeks before vanishing into deep space. Newly digitized records from that campaign show hints of periodic brightness variations matching the mathematical signatures we now associate with potentially engineered systems. These historical searches face significant challenges because observational techniques were less sophisticated in previous decades. Many potentially important observations exist only as photographic plates or analog recordings, requiring extensive digitization and enhancement before modern analysis methods can be applied. The process often proves frustrating, as tantalizing hints of anomalous behavior remain forever trapped at the resolution limits of older instruments. The theoretical framework for understanding objects like 3i Atlas has evolved rapidly as physicists and engineers grapple with the implications of confirmed artificial origin. If this visitor represents technology rather than natural phenomena, it demonstrates capabilities that redefine our understanding of what might be achievable, even for highly advanced civilizations operating across interstellar distances. The precision timing alone suggests computational systems that maintain accuracy across geological timescales, while functioning in the harsh environment of deep space. The coordinated multi-wavelength emissions indicate control mechanisms that can simultaneously manage optical, thermal, and chemical processes with clockwork regularity. The positional oscillations require thrust systems that operate with mechanical precision, despite the countless perturbations that should randomize any natural motion over millions of years. Some theoretical models propose that sufficiently advanced civilizations might develop technologies capable of manipulating space-time geometry directly, creating propulsion effects through controlled gravitational field variations, rather than conventional reaction mass expenditure. Such systems would leave minimal observable signatures while providing the precision control needed to maintain complex orbital patterns across astronomical timescales. The communication aspects of 3i Atlas's behavior have generated intense speculation about whether the observed patterns represent intentional signaling or merely operational byproducts of internal systems. The mathematical relationships between different periodicities contain information density that could theoretically encode technical specifications, navigation data, or messages designed for observers sophisticated enough to detect and analyze such subtle patterns. Decoding efforts have focused on extracting potential information from timing variations, frequency relationships, and phase correlations between different emission types. While no definitive messages have been identified, the complexity and organization suggest information content far exceeding what random natural processes would typically produce. The nested periodicities and apparent error correction properties embedded within the timing patterns bear striking resemblances to optimal encoding schemes developed for long-distance data transmission. The philosophical implications stretch far beyond technical questions about 3i Atlas's construction to encompass fundamental questions about intelligence, consciousness, and purpose operating on cosmic scales. If this object represents deliberate engineering, it demonstrates that intelligence capable of interstellar projects has existed somewhere in our galaxy for millions of years, operating on timescales that dwarf the entire history of human civilization. The motivations behind such an ambitious undertaking remain entirely speculative. 3i Atlas could represent scientific exploration, serving as an automated probe designed to collect data about stellar systems and any civilizations they might harbor. The subtle signaling behavior could be specifically engineered to identify species that have achieved sufficient technological sophistication to detect and analyze complex patterns in astronomical observations. Alternatively, this visitor might function as a navigation beacon or communication relay, forming part of a galactic infrastructure that enables coordination between widely separated civilizations. The precise timing and positional control could facilitate long-range communication or navigation systems operating across interstellar distances using principles we don't yet comprehend. Perhaps most poignantly, 3i Atlas might represent abandoned technology from a civilization that no longer exists, continuing its mission autonomously according to programming established millions of years ago by creators who have since vanished or evolved beyond recognition. In this scenario, we could be observing the final traces of intelligence that once flourished among distant stars but left only these silent messengers as evidence of their former existence. The detection methodologies developed during the 3i Atlas investigation are already being integrated into current astronomical surveys. The Vera Rubin Observatory, achieving full operational status this year, will survey the entire visible sky every few nights with unprecedented sensitivity and precision. The data processing pipelines have been specifically modified to automatically flag objects, displaying characteristic signatures associated with potential artificial origin. These search parameters include multiple criteria that must be satisfied simultaneously to minimize false positives while maintaining sensitivity to genuinely anomalous objects. Precise periodicities in brightness or position, unusual chemical compositions, systematic correlations between different types of emissions, and trajectory characteristics suggesting active control all serve as potential indicators of engineered origin. The challenge lies in establishing threshold criteria that minimize false alarms while remaining sensitive to genuinely extraordinary phenomena. Natural objects occasionally display some suspicious characteristics through coincidental circumstances, making it crucial to identify combinations of features that are individually possible but collectively improbable. Patterns requiring multiple unlikely coincidences to occur simultaneously in natural systems. The international coordination established during the 3i Atlas campaign has created new protocols for rapid response to potentially significant discoveries. Communication networks now exist for immediately alerting the global astronomical community when objects with suspicious characteristics are detected, enabling coordinated follow-up observations before these fast-moving visitors disappear beyond observational reach. Data-sharing agreements developed during this investigation have established precedents for making observational information immediately available to researchers worldwide, regardless of institutional or national affiliations. This collaborative approach accelerates analysis while ensuring that multiple independent teams can verify findings and contribute diverse analytical perspectives. The technological innovations driven by 3i Atlas research continue advancing capabilities in astronomical instrumentation and data processing. New techniques for detecting subtle periodicities in noisy datasets, methods for coordinating observations across multiple wavelengths and observational platforms, and approaches for modelling complex multi-parameter systems have all emerged from efforts to understand this extraordinary object. Computational resources devoted to this analysis have demonstrated the value of applying supercomputing capabilities to astronomical data processing. The complex statistical analyses required to confirm periodicities and model multi-wavelength correlations demand computational power rivaling major physics experiments. These capabilities are now being applied more broadly to other areas where complex periodic phenomena require sophisticated analysis techniques. The educational impact has transformed how astronomy students learn about scientific methodology and the evaluation of extraordinary claims. 3i Atlas serves as a comprehensive case study in maintaining rigorous scientific standards, while remaining genuinely open to possibilities that could revolutionize our understanding of the universe. The careful balance between healthy skepticism and authentic curiosity characterizing this investigation provides a template for approaching other potentially paradigm-shifting discoveries. Public engagement surrounding 3i Atlas has demonstrated both the benefits and challenges of communicating ongoing scientific research to general audiences. The inherent uncertainty in scientific investigation, where conclusions evolve as new evidence accumulates, requires careful explanation for audiences accustomed to definitive answers and clear explanations. Media coverage has generally maintained appropriate balance between conveying genuine excitement within the scientific community and emphasizing the preliminary nature of many conclusions. The crucial distinction between intriguing observations and confirmed discoveries continues being important as analysis proceeds and additional data becomes available. Cultural implications extend beyond science communication to influence broader discussions about humanity's place in the universe and our readiness for potential contact with other intelligences. The methodical, evidence-based approach being taken to evaluate 3i Atlas provides a valuable model for how our species might handle even more direct evidence of extraterrestrial intelligence should such evidence emerge in the future. The timeline for reaching definitive conclusions continues being governed by the object's observational accessibility and the time required for thorough analysis of accumulated datasets. As 3i Atlas moves farther from the Sun and becomes increasingly difficult to study with current instruments, emphasis shifts from gathering new observations to extracting maximum information from existing data. Long-term monitoring programs will continue tracking this visitor for as long as technically feasible, watching for any behavioral changes that might provide additional insights into its nature and purpose. These extended observations will test whether the remarkable precision we've documented represents a stable characteristic or might evolve as the object encounters different environmental conditions. The archive analysis continues revealing additional subtle characteristics that add complexity layers to an already extraordinary puzzle. High-resolution spectroscopic observations have identified molecular emission lines that don't quite match laboratory standards, suggesting either exotic environmental conditions or systematic velocity shifts that could indicate internal motion within the object's structure. Polarization characteristics of reflected light continue evolving in patterns that correlate with all other periodic phenomena. The systematic rotation of polarization angles suggests surface features with preferred orientations that maintain precise alignment despite the object's motion through space. Natural weathering processes would be unlikely to preserve such organized surface structure over the timescales implied by interstellar travel. Thermal infrared observations have revealed heat distribution patterns that persist despite changing solar illumination angles. Temperature variations that should respond directly to solar heating instead follow the internal timing of the object's other periodicities, suggesting thermal management systems operating independently of external energy input. Dust production analysis shows that particles ejected from 3i Atlas maintain more uniform size distributions than typical comet debris. The narrow range of particle sizes optimizes light scattering efficiency while minimizing mass loss, a combination that would be valuable for systems designed to remain visible over long periods while conserving material resources. Chemical evolution of gases in the coma continues defying standard photochemical models. Molecular species that should break down rapidly under solar ultraviolet radiation instead persist longer than expected, while others disappear more quickly than theoretical predictions suggest. These discrepancies could indicate catalytic processes or electromagnetic field effects that modify normal photochemical reaction rates. Multi-wavelength coordination between emissions at vastly different energy scales has reached precision levels that challenge our understanding of how natural systems maintain coherence across such diverse physical processes. Radio variations correlate with optical changes, which correlate with infrared thermal signatures, which correlate with subtle shifts in high-energy particle detection rates. Phase relationships between these different emission types remain locked with accuracy rivaling atomic clocks. When optical brightness reaches maximum, radio emissions, thermal signatures, and chemical emission rates all follow predictable sequences with timing precision, suggesting coordination mechanisms of extraordinary sophistication. Gravitational wave monitoring continues showing tantalizing correlations between background noise patterns and 3I Atlas's periodic behaviors. While no direct gravitational wave signals have been detected from the object itself, subtle correlations with sensitive instruments suggest possible interactions through mechanisms that remain poorly understood but could indicate exotic physics operating at macroscopic scales. Neutrino detection experiments have accumulated additional data strengthening evidence for particle flux variations correlated with the object's optical cycles. Statistical significance has improved as more detection events accumulate, though correlations remain at levels requiring careful analysis to distinguish from background fluctuations. Quantum coherence properties detected in electromagnetic emissions continue suggesting processes that maintain phase relationships across spatial scales much larger than typical quantum decoherence lengths. These quantum signatures could indicate technology manipulating matter at the quantum level to produce coordinated electromagnetic outputs with precision exceeding classical physics limitations. Information theory analysis has identified hierarchical organization in timing patterns that maximizes information density while maintaining error correction properties. The nested periodicities contain redundancy and structure characteristic of optimized communication protocols rather than random natural processes. Systems engineering analysis concludes that while 3I Atlas's characteristics would require technological capabilities far beyond current human achievements, they represent extensions of known physical principles rather than violations of fundamental laws. The precision, longevity, and coordination observed would demand engineering philosophies prioritizing robustness and reliability over performance optimization. Fault tolerance mechanisms required for such systems to operate reliably over millions of years would need to incorporate self-diagnosis, automatic repair, and graceful degradation capabilities exceeding anything currently achievable. These requirements push boundaries of what might be possible even for highly advanced technological civilizations. Power management systems would need to harvest energy from environmental sources while maintaining sufficient reserves for active control functions. Potential mechanisms might involve exotic energy conversion processes extracting useful work from cosmic radiation, magnetic field variations, or quantum vacuum fluctuations through principles remaining theoretical in our current understanding. Material science requirements would demand substances maintaining structural and functional integrity across temperature ranges from near absolute 00 to several hundred Kelvin, while withstanding millions of years of cosmic ray bombardment. Surface coatings would need to preserve optical properties despite micrometeorite impacts and chemical erosion from reactive species in interstellar space. Computational architecture would require processing capabilities remaining functional across geological timescales, while maintaining precision necessary for coordinating multiple periodic systems. This would involve error correction methods, redundancy systems, and self-repair mechanisms operating at sophistication levels, representing theoretical limits of achievable technology. The international collaboration studying 3I Atlas has evolved into the most comprehensive observational campaign ever mounted for a single solar system object. Telescopes across 6 continents coordinate observations to maintain continuous coverage as Earth's rotation carries individual facilities in and out of optimal viewing positions. Data analysis efforts involve computational resources from supercomputing centers worldwide, running continuous simulations attempting to model the object's behavior under various natural and artificial scenarios. The complexity of observed phenomena requires interdisciplinary cooperation between astronomers, physicists, engineers, and computer scientists working together to understand measurements that don't fit comfortable categories. Peer review processes have adapted to handle unprecedented discovery paces while maintaining rigorous standards for scientific verification. Preliminary findings are shared through preprint servers, enabling rapid communication. while formal peer review proceeds in parallel, ensuring extraordinary claims receive appropriate scrutiny before acceptance as established science. The search for additional objects with similar characteristics has expanded to include reanalysis of historical observations using modern detection techniques. Several candidate objects have been identified showing some features reminiscent of 3I Atlas, though none display the complete complement of anomalous behaviours making this visitor so extraordinary. Detection criteria developed for identifying potentially artificial objects are being incorporated into automated survey systems that will scan future observations for suspicious patterns. The goal involves establishing objective, quantitative methods for distinguishing between genuinely anomalous objects and natural phenomena that happen to display unusual characteristics through coincidental circumstances. Statistical frameworks for evaluating artificial versus natural origin continue evolving as more sophisticated analysis techniques are developed and applied to accumulated data. The challenge lies in establishing threshold criteria that minimize false positives while maintaining sensitivity to genuinely extraordinary phenomena that could represent the most important discoveries in human history. As we stand at this crossroads between the known and the unknowable, 3I Atlas continues its ancient dance through our cosmic neighbourhood, carrying with it implications that stretch far beyond the comfortable boundaries of conventional astronomy. The patterns persist with mathematical perfection, the precision endures across millions of miles of space, and the questions multiply with each passing observation. Whether this extraordinary visitor ultimately proves to be nature's most perfectly engineered coincidence, or our first confirmed encounter with intelligence from beyond the stars, its passage through our solar system has already transformed our understanding of what might be possible in the vast expanse between the stars. The universe, it seems, still holds secrets that can humble our assumptions and expand our conception of what exists in the cosmic ocean that surrounds our small planetary home. The precision doesn't stop there. When you examine the energy requirements for maintaining these oscillations, the numbers become even more extraordinary. To create the observed positional shifts through conventional propulsion would require thrust adjustments consuming approximately 1 kilogram of material per cycle. Over the course of 3I Atlas's presumed multi-million-year journey through interstellar space, this would demand fuel reserves exceeding the object's estimated total mass by factors of thousands. Either we're witnessing propulsion efficiency that approaches theoretical impossibility, or this visitor operates on principles we haven't discovered yet. The brightness variations present equally puzzling energy dynamics. If these pulses result from controlled reflection of sunlight, they would require surfaces that can be oriented with arc-second precision, while the object rotates through space. The mechanical systems needed for such control would involve sensors detecting orientation changes, processors calculating corrections, and actuators implementing adjustments with accuracy that rivals our most sophisticated spacecraft. All of this would need to function flawlessly for geological time periods without any possibility of maintenance or repair. What makes these requirements even more staggering is the environment 3I Atlas has endured during its journey between the stars. The interstellar medium might seem empty, but at the velocities these objects travel, even individual atoms become cosmic sandpaper, gradually eroding surfaces and altering mass distributions over millions of years. Any natural object subjected to this constant bombardment should develop asymmetries and irregularities that would disrupt precise rotational patterns within centuries, not maintain them across eons. The isotopic analysis has revealed another dimension of strangeness that compounds the mystery. Advanced spectrometers studying 3I Atlas's emissions show carbon isotope ratios that don't match patterns typical of objects formed in stellar environments. Instead of the carbon-12 to carbon-13 signatures we see in comets from our solar system, or meteorites from known populations, this visitor displays isotopic fingerprints suggesting either exotic formation conditions or processing that occurred after its initial creation. These isotopic anomalies could result from nuclear processes operating within the object itself. Cosmic ray bombardment over millions of years can alter isotope ratios, but usually in predictable ways that leave characteristic signatures. 3I Atlas shows patterns that don't match standard cosmic ray processing models, indicating either unusual exposure conditions during its interstellar journey or internal mechanisms that selectively concentrate specific isotopes through processes we don't understand. The temporal evolution of these isotopic signatures adds another layer of complexity that defies easy explanation. Rather than remaining constant as we'd expect from passive cosmic ray processing, the ratios appear to change subtly over observation periods lasting weeks. These variations correlate with the object's brightness cycles, suggesting that whatever drives the optical pulses also influences the isotopic composition of ejected material in ways that require active control mechanisms. Neutrino detectors positioned around the globe have been monitoring for exotic particle emissions from 3 atlases direction, with results that hover tantalizingly at the edge of detection. While no definitive signals have been confirmed above background noise levels, there are hints of correlation between the object's brightness cycles and subtle variations in neutrino flux measurements. These correlations remain at the threshold of statistical significance, requiring months of additional data to confirm or refute, but they suggest the possibility of high-energy processes operating within this mysterious visitor. The plasma physics surrounding 3I Atlas's interaction with the solar wind reveals additional anomalies that challenge conventional understanding. As charged particles from the Sun encounter the object's coma, they should create predictable patterns of ionization and magnetic field distortion. Instead, spacecraft magnetometers detect field configurations, suggesting the object somehow channels or redirects solar wind in ways that don't match standard models of comet plasma interactions. These magnetic anomalies could result from metallic components within the object, creating localized field concentrations, but the field patterns show the same periodicity as the optical variations, suggesting active control rather than passive magnetic effects. Natural magnetization would remain constant or vary randomly with thermal cycling, not pulse in precise synchronization with brightness changes that occur with clockwork regularity. The patterns continue their cosmic dance, precise as mathematics, regular as the most sophisticated clockwork ever conceived. As 3I Atlas moves deeper into our solar system, carrying with it questions that challenge everything we thought we knew about the space between stars, we find ourselves at a crossroads that will define how humanity approaches the unknown. Whether this extraordinary visitor ultimately proves to be nature's most perfectly balanced accident or our first confirmed encounter with intelligence from beyond our world, it has already transformed our understanding of what's possible in the universe that surrounds us. The mystery deepens with each observation, each measurement, each attempt to fit these impossible patterns into comfortable explanations, reminding us that the cosmos still holds secrets capable of humbling our assumptions and expanding our conception of what might exist among the stars.